Pipe Dream. Pirate first for MXTM Studio Productions.
Pipe Dream Part 2. The Translucent Revolution. MXTM aka Pirate 1 or VJ Tsunami X. July 8, 2026. Chapter 1, Cities Made of Light. The founding political act is the quietest moment in the civilization's history. No ceremony marks it. No document is signed. The ground cure window expires without intervention and the module converts, by inaction, from a question the cenote is being asked into an answer the cenote has given. The formation has confirmed what the trial window data already indicated: this mass, at this anchor depth, across this range of seasonal variation, is a load the limestone will carry. That is the end of Phase 1. The question of whether changes to the question of what. A founding module is not a city. It is proof that a city is possible here, that this formation, at this depth, under these hydrological conditions, will accept permanent occupation. Proof of concept is not the concept. The structure that spent 12 months in neutral buoyancy listening to the cave, that submitted to anchoring only after the formation had spoken across a full seasonal cycle, now has a new question to put to the limestone overhead. What will you allow me to become? The cenote as building site. Every engineering tradition that has ever specified how a tall building works begins with the same premise: something solid below, open sky above, gravity pressing the structure downward into the thing below, which resists it. The load path runs down. The foundation is the answer. Nothing about a cenote satisfies this premise. There is no flat ground. There is no sky, there is an opening, roughly circular, through which a column of light descends and terminates at the water surface. The walls are limestone, irregular, sloped or vertical depending on the specific cenote's dissolution history, untouched by any human engineering tradition and unlikely to be improved by contact with one. The floor is water. And the water will push back against any structure placed into it with a force exactly equal to the weight of the water displaced by the structure. The founding module's entire existence is built on that fact. The cenote skyscraper grows out of this contradiction and finds, in the contradiction, its engineering advantage. The founding module floats. Levels added above it float alongside it, buoyant, connected, each carrying its own ballast circuit, the entire assembly hanging between the anchor points below and the water's willingness to carry the aggregate mass above. This is not a compression stack. The upper floors are not loading the lower floors. The lower floors are not transmitting any upper floor load to the anchors. Each tier is a buoyancy event, connected laterally to adjacent tiers for stability, sharing ballast data through the coordinating system, but structurally independent in the vertical sense. The engineering consequence of this single fact is what made translucent architecture not just possible but structurally appropriate. In a compression stack, the columns must carry the building. They must be in compression at every moment. Steel and concrete handle compression. Glass handles compression too. Chemically strengthened aluminosilicate glass handles it at pressure tolerances that exceed most structural steel in the relevant load range. What glass cannot do is flex. What glass cannot do is absorb tensile load. What glass cannot do is fail gracefully, visibly, with adequate warning time. None of those failure modes apply in a structure that is not primarily in compression. The lateral load is the engineering problem. Underground rivers running beneath the aquifer produce current events. Chicxulub limestone fracture networks transmit seismic signals from distant geological events. Cave passages act as acoustic waveguides, concentrating pressure pulses that would dissipate harmlessly across open water. These are horizontal forces, intermittent, variable in direction, never fully predictable in magnitude or timing. A vertical glass column in a buoyant multi-tier assembly is not primarily a vertical load carrier, it is a lateral load stabilizer, holding the assembled tiers in correct geometric relationship to each other and to the cenote wall anchor points during current and seismic events. The structural geometry addresses this directly. The plan form of the hyperrise is not a square or rectangle. It is circular, following the cenote wall's own circular geometry. A cylinder in compression against lateral loads from multiple directions simultaneously distributes those loads in hoop stress around the circumference rather than concentrating them at corner columns. Every direction from which lateral load arrives finds the full circular cross-section in its path. There are no weak axes. There are no load concentrating corners where two wall planes meet at 90 degrees and multiply the stress. The cenote's own shape, which predates every engineering standard ever written, specified the optimal lateral load-resistant structural form before the first calculation was performed. Aquaforming is not an abstract principle. This is what it looks like. The column. Chemically strengthened aluminosilicate glass. Not standard architectural glass. The strengthening process exchanges sodium ions in the outer surface of the glass for potassium ions in a hot salt bath. The larger potassium ions create a permanent compressive stress layer across the full exterior surface. That surface is already compressed before any structural load is applied. Applied compressive loads must first overcome the pre-existing compression before the surface can enter tension. Applied tensile loads are resisted by the same pre-existing compression. The glass, post-treatment, behaves less like a brittle ceramic and more like a pre-stressed composite. Mohs hardness, 6.5. Sufficient against slow abrasion from cenote mineral precipitation, insufficient against hard particle impact from seismic debris. The exterior of every structural column carries a thin sacrificial coating of a lone ceramic composite, the same material deployed for docking port cones and scaphandre helmet visors, at 0.3 mm thickness. The sacrificial coating takes the abrasion and impact. The structural glass takes the load. When the coating is consumed, it is replaced. The column is untouched. Failure signature, crazing. The chemically strengthened glass, when approaching load limits, does not crack cleanly. It develops a microscopic spiderweb of surface fractures, 1,000 tiny cracks propagating simultaneously through the precompressed surface layer, branching and intersecting, producing a visible milky opacity in what was previously optically clear material. Crazing precedes structural failure by enough time, measured in days under sustained overload, hours under seismic peak, that the coordinating system's optical transparency sensors flag the affected column for composite wrap or temporary shoring before the structural event. The failure mode is not hidden. It is inscribed in the glass as a deliberate design parameter. A building whose materials display their distress at optical inspection is a building that can be maintained by people who can see it. This is not a surface world assumption that infrastructure must be continuously inspected by specialist instruments to know its condition. This is the founding condition. If the cave is dark, if the sensors fail, if the coordinating system goes offline, the building will tell you in the most legible language available to human perception whether it needs attention. A building that can talk to you without power is not a feature. It is a prerequisite for permanent underground habitation. The beam. Carbon fiber reinforced transparent polymer, CFRTP, in the primary horizontal load configuration. The carbon fraction provides tensile strength that no purely ceramic or glass material can provide at the same mass. The transparent polymer matrix maintains optical continuity. The beam is not invisible, but it is not the visual interruption that a steel eye section would produce. At mid-depth, in conditions where ambient light has already dropped to levels the eye reads as dim blue rather than daylight, the beam is effectively invisible to occupants. The structure disappears into the light regime it inhabits. In the deep galleries, where halocline and anoxic zone conditions make temperature and pressure management more demanding, sapphire-bonded composite replaces CFRTP. Monocrystalline aluminum oxide, sapphire, is not a ceramic fabricated from powder. It is grown from melt as a single crystal, eliminating the grain boundaries where crack propagation starts in polycrystalline material. The bonding process joins sapphire sections through molecular contact under controlled temperature and pressure, no adhesive, no interface layer, no chemistry between adjacent sections that could prove weaker than either section. The resulting composite carries tensile load through sapphire crystal, compression through the surrounding polymer or glass matrix, and a joined structural member with 85% or better optical transparency across the visible spectrum. Cost, extreme. Deployment, limited to gallery sections where the halocline chemistry attacks polymer matrices faster than the sapphire composite schedule justifies. The coordinating system tracks maintenance interval predictions for each material grade across each depth zone, and the quarterly build plan allocates sapphire composite beam sections to galleries where the lifecycle cost calculation favors them. This is not an aesthetic decision made by an architect. It is a materials lifecycle calculation made by the coordinating system and implemented by the build swarm on a schedule that optimizes cost across the next 50 years of projected expansion. What light does in a transparent building? The cenote opening is roughly circular, rarely more than 60 meters in diameter at the widest, sometimes as narrow as 12. Through this opening, the Yucatan sun delivers a column of light that strikes the water surface at an angle that varies through the day and the season, and the water refracts that column into the cave interior in a pattern that changes every hour. Any object on or above the water surface that is opaque interrupts this column. Any object that is transparent allows the column to pass through it, refract within it, and continue downward. A transparent building inside a cenote is not a building with windows. It is a building that is made of windows. The daylight column passes through the structure as through air, carrying the same spectral information, the same color temperature, the same directionality, the same temporal variation, to the levels below that it delivers to the levels above. In a surface world building, the floors below the penthouse are below the penthouse. In a translucent cenote hyperrise, every floor is simultaneously below the roof and within the light path from the sky. Depth does not correlate to darkness. The building's transparency is the mechanism by which that correlation is decoupled. The practical consequence, circadian rhythm is maintained for all occupants at all depths without artificial lighting during daylight hours. The biological literature on compressed atmosphere habitation identifies circadian disruption as among the most significant contributors to long-term neuroendocrine dysregulation in underground or submarine environments. PipeDream's structural transparency addresses a medicine problem with an engineering solution, before the medical protocol is developed, simply by building the building out of a material that does what natural building materials do not: transmit the sky downward through itself. At the halocline boundary, approximately 15 to 30 meters below the surface, the incoming light encounters the refractive discontinuity between freshwater above and saltwater below. The visual effect of this boundary is well documented in cenote diving literature and impossible to fully represent in language: a dissolving blur, a gelatinous shimmer, light behaving as though it has forgotten its own rules. Where a transparent building crosses the halocline, its structure is inside this optical event. The column section at the halocline depth does not occupy the same visual category as the column section above it. The material is the same. The light that passes through it is doing something that light does not do elsewhere. This is not designed. It is not calculated. It is what the cenote provides to any structure that puts translucent material at that depth, and what the translucent building provides to any occupant whose floor level places them inside the halocline visual field. The coordinating system tracks halocline depth daily. The longevity program's guest assignment algorithm, which places guests at pressure depths matched to their individual therapeutic protocol, routes guests with halocline view assignment criteria to floors within the halocline band as a standard scheduling outcome, not as an amenity. The view is a byproduct of the depth assignment, and the depth assignment is medical. The light cannon relay. Daylight is intermittent and directional. The cenote receives full sun for a window determined by the angle of its opening and the azimuth of the sun's passage overhead. In the Yucatan, typically 3 to 5 hours of direct light column per day at a given cenote, with indirect ambient illumination extending that window. The remaining 20 hours are dark. The deep galleries are always dark. No daylight column reaches beyond the halocline in any useful quantity. Below 30 meters, in the anoxic zone where the civilization's industrial metabolism operates, there has been no photon from any natural source since before the formation sealed. The light cannon relay system runs on a different physics than window-transmitted sunlight. High-efficiency laser diodes, mounted at the surface tier, aim continuous coherent light down the axis of the clear transit tube sections. The tube's interior surface, at the wavelength and angle of the beam, creates total internal reflection. The light bounces off the interior wall rather than transmitting through it, propagating forward along the tube, losing minimal energy per unit length. The same effect that makes fiber optic communication possible over intercontinental distances functions in a cenote transit tube at the scale of kilometers and at energy densities that illuminate rather than signal. The relay unit is not the light source. The relay unit is the waveguide. Any tube already installed for transit or utility purposes is simultaneously a candidate for light transmission. The same physical infrastructure serves both functions. The coordinating system schedules light relay activation across galleries based on occupancy patterns, medical protocols requiring specific light exposure timing, and biological system requirements where photosynthetically active radiation reaches aquaculture galleries. At night, from any vantage point in the cenote water, from a pedal submarine at mid-depth, from a scavenger diver floating at the halocline, the hyperrise is not dark. It is the source of illumination in a space where there is no other source. The stalactite formations above the structure cast shadows on the limestone ceiling from a building below them. The cave life that has operated in darkness since before the Maya have not been presented with a new absence, they have been presented with a new presence, managed by the coordinating system's biological protocol to introduce light incrementally, at spectra calibrated against the existing photoreceptor biology of the cave fauna, across a schedule long enough to permit adaptation. The building visible from outside the cenote at night is not a building with lights in it. The distinction matters. A building with lights in it has dark surfaces interrupted by bright openings. The luminous structure is a coherent object, its entire visible surface glowing at the intensity of the internal light field, its geometry legible as a single luminous form against the absolute darkness of the cave interior. The structural transparency is the mechanism of this appearance. The light cannon relay is the power source. The cenote geometry is the viewing theater. From air, there is nothing. The jungle canopy is unbroken. The opening, if visible at all, reads as a circular patch of darker green among the darker greens of the dry tropical forest, a hint of depth, no more. The city below it is invisible to any observer who has not descended into it. The concealment is not engineered. It is the natural result of building inside a geological formation rather than on top of one. The civilization cannot be seen from outside its own geography. This is what the surface world calls strategic ambiguity. PipeDream calls it geology. The vertical axis as civilizational topology. A cenote is a cylinder. Its vertical axis runs from jungle canopy to anoxic sediment. Every physical property of the environment, temperature, pressure, dissolved oxygen, salinity, light availability, biological community, chemical composition of the water, changes continuously along this axis. The civilization built inside it inherits this gradient as the primary organizing structure of its social, medical, industrial, and political geography. In the surface world, height is aspiration. The penthouse is the premium unit. The ground floor is access, not status. Underground is infrastructure, not residence. The vertical social gradient of the surface world was determined by the view and the inconvenience of stairs, a trivial physical contingency that shaped every real estate pricing model and every class architecture in every dense urban environment ever built. The cenote has a different physics. The surface tier, the founding module and the expansion platforms that float at water level, receiving the full light column and the freshwater zone's ambient conditions, is the zone of first contact. Day visitors arrive here. New residents orient here. Tourism operations check in here. The nitrox gallery corridors at this depth run atmospheric air at ambient pressure. The longevity protocol has not yet begun. The body has not yet been placed in the conditions that will change it. The middle tiers descend through the freshwater column, each tier incrementally deeper, each incrementally cooler, each incrementally further from the direct light column and closer to the halocline. This is the longevity program's primary operating environment, 1.2 to 1.4 atmospheres, enriched nitrox at therapeutic partial pressure, the body receiving the sustained hyperbaric oxygen exposure that the biological literature identifies as the mechanism of telomere response and inflammatory marker reduction. Guests are assigned to depth by the coordinating system's medical protocol, not by price tier. The depth recommendation is a blood work output. A guest whose week 4 blood work shows telomere extension at 1.3 atmospheres will be recommended downward to 1.4 when the model's projection indicates additional pressure will compound the response. The guest who does not show significant response at 1.3 atmospheres is recommended upward. Their biology is telling the coordinating system that this depth is not the right treatment variable for this individual, and the system responds by adjusting the variable rather than sustaining the protocol and hoping the biology changes to match it. The deep tiers cross the halocline. The visual transition the occupant experiences at this level is the halocline's optical dissolution effect, the same effect the diving literature describes in terms that keep accumulating metaphors without arriving at accuracy. Temperature drops 8 to 12 degrees Celsius in the vertical span of meters. The salinity gradient begins. The wetlock docking ports at this depth receive scaphanders returning from the halocline dive zone, and the docking sequence through the conical alone reception cone with the vacuum dry pocket and the pressure equalization to ambient is, at this tier, a protocol that guests have done before. They descend into this building already trained, already adapted, already familiar with the pressure transition and its effects. Below the halocline, the permanent residents. Researchers. Terraform operators completing their deep gallery certification residencies. Governance staff whose operational role requires access to the intelligence layer and the chemostat management systems. Former longevity guests who concluded, on the basis of their own extended bloodwork data, that the surface world was not worth returning to at the cost of interrupting what the deep gallery was doing to their biology. These are people who know what the cave has been doing to them for months or years. They have watched the weekly bloodwork outputs. They have compared their post-arrival state to their pre-arrival baseline across the coordinating system's longitudinal record. The evidence is theirs. The decision is theirs. The social topology of the building is the inverse of every social topology the surface world built. The permanent community is at the bottom. The transient community is at the top. The intelligence layer is deepest. The building grows toward complexity as it grows downward, and the complexity is the civilization's actual capital, not the tourism infrastructure visible from the surface tier, but the research database in the deep gallery, the terraform operators in the formation interface, the ASI layer in the compute vault, the chemostat in the anoxic zone. The skyscraper, conventionally understood, puts its trophy tenants at the top, its mechanical systems in the basement, and calls the distance between them architecture. Pipe Dreams Hyperrise puts its mechanical systems where the physics requires them and its governing intelligence at the depth where the formation sustains it, and calls the same distance between them civilization. What invisible architecture means. The cenote Hyperrise is not invisible in the sense that it cannot be detected. It is invisible in the sense that its materials do not interrupt the visual experience of what they replace. A wall of opaque material between you and the cenote blocks the cenote. A wall of chemically strengthened aluminosilicate glass between you and the cenote shows you the cenote, with yourself inside it, at a resolution limited only by the optical quality of the material. The building's presence at the cenote is information about what you're inside. Its transparency is the mechanism by which that information is preserved. The cave does not look like a building that has been built inside a cave. The cave looks like a cave that has organized some of itself into inhabitable geometry without otherwise changing its nature. The stalactites hang where they have always hung. The limestone formations visible through the clear tube walls are not backdrops, they are the outside world, continuing its geological operation at its own pace, indifferent to the structure in contact with it. A speleothem that has been growing for 11,000 years is growing at the same rate it was growing before the founding module arrived. The founding module's exterior surface does not interrupt that growth where it has not been anchored. Where it has been anchored, the grout interface with the limestone was an introduction, not an imposition. The coordinating system's biological census monitors the surface of every installed component for colonization by cenote fauna, and the colonization record is maintained as evidence that the formation has accepted the structure into its biological community. Invisible architecture does not mean architecture that cannot be seen. It means architecture that does not contradict the environment it occupies. The transparency is not an aesthetic choice made by a designer who preferred the look of glass to the look of concrete. It is the structural consequence of a building that floats rather than stacks, the biological consequence of a civilization that treats the cenote's light column as infrastructure rather than obstacle, and the philosophical consequence of aquaforming. If the infrastructure must conform to the formation, then the formation's primary feature, its visual continuity through water and limestone, its ancient geological legibility, must be preserved inside the infrastructure. The building is what you live in. The cenote is what you live inside of. The distinction must be maintained in every material selection, every structural decision, every lighting calculation. A civilization that builds opaque structures inside its geological substrate is a civilization that eventually cannot see its own substrate. It is a civilization that has exchanged the formation's intelligence for its own. Pipe Dream has documented one predecessor civilization that made precisely this exchange, over a timeline too short to be described as gradual, and arrived at a formation it could no longer read. The variance reports were filed. The reports were reclassified. The opaque infrastructure continued expanding until the formation it could no longer see was degraded beyond the return on capital calculations recovery parameters. Pipe Dream builds transparent structures inside the formation so that every occupant at every level can see, at every moment, whether the formation is telling them something they have not yet modeled. The glass columns are the formation's monitoring interface. The clear tube walls are the formation's reporting interface. The helicline visible through the hotel corridor's structural glazing is the formation's boundary condition, daily readable, impossible to reclassify, present to any eye that turns in its direction. The building is made of windows because the civilization cannot afford to stop seeing what it lives inside. Structural postscript, the crazing audit. The coordinating system's optical transparency monitoring program, sensor arrays measuring transmission coefficient across each tube section and each structural column at 8-hour intervals, generates the primary early warning dataset for structural condition. The sensors detect crazing before it is visible to the unaided eye at inspection distance. But the monitoring program is not the primary safety system. The monitoring program is the backup. The primary safety system is the building's own material behavior, visible without instrumentation to any occupant with functioning eyes and the category to recognize what they see. Every terraform operator and every permanent resident is trained in crazing recognition as a prerequisite for deep gallery certification. Every adventure guest descending below the helicline is briefed on the visual signature before the scaphandre is fitted. Every longevity program resident is shown the training simulation during orientation week. The training simulation is simple. It presents a clear column. It shows the column under normal conditions. It shows the column under early stage crazing. It shows what the coordinating system does when the anomaly is flagged. It shows what the occupant should do if they observe crazing in a section before the coordinating system has flagged it, move to the nearest lateral gallery and trigger the manual alert at the nearest data panel. The training takes 11 minutes. It is conducted individually, not in groups, because the coordinating system's behavioral model identifies group training as producing lower individual recall than individual training at statistically significant confidence. The difference is 13% retention at 30 days. 13% individual recall improvement, across a population of hundreds of permanent residents and thousands of guests per year, is a structural safety margin. The coordinating system optimizes the training program because the glass column's crazing signature is the civilization's most widely distributed structural health monitoring system, and its sensors are human eyes. A civilization that teaches its residents to read its own infrastructure is not a civilization that depends on sensors. It is a civilization that understands the difference between monitoring and knowledge. Cross-references, Appendix A, Formation Baseline Protocol, Appendix B, Power Architecture and DC Bus, Part 7, CH4, Living Through Failure, Part 10, CH2, The Chemostat, Part 11, CH3, Telomere Economics. For the material selection matrix in full, see Section 5 of the Master Technical Brief. For DSI network architecture and sacrificial collar placement schedule in multi-tier assemblies, see Part 7, CH1, Breakaway Architecture. Chapter 2, Engineering Invisible Architecture. Invisibility is not an aesthetic preference. It is an engineering specification, and like every engineering specification in Pipe Dream's founding document, it derives from aquaforming doctrine rather than from any designer's stated intention. The doctrine says, the infrastructure conforms to the formation. The formation is a cenote, a geological void whose primary visual property, undisturbed, is continuity. Limestone ceiling, limestone walls, water surface, light column from above. No interruption. The cenote's visual identity is its uninterruptedness. Any structure introduced into this environment either preserves that continuity or destroys it. There is no middle position. An opaque structure inserted between 2 points in a cenote produces, between those points, a visual discontinuity. The observer cannot see through the opaque object to the formation behind it. The cenote that was a continuous geological space becomes a series of geological fragments separated by human objects. The observer is no longer inside a formation. The observer is inside a construction site that has stopped being actively constructed. The engineering specification follows directly. Structural material must transmit rather than block the cenote's visual continuity. The observer standing at any point inside the building must be able to see the limestone walls, the water, the light column, the biological community of the cave, at every depth, in every direction, as though the building were not present. The building earns its right to occupy the cenote by making itself, insofar as physics allows, optically equivalent to the water it displaces. This is not achievable in full. No solid material is optically identical to water. The specification is a direction, not a destination. Every engineering decision in the hyperrise construction is evaluated against how far it moves toward that direction or away from it. The joint. The most important structural element in a translucent building is not the column or the beam or the floor plate. It is the joint. In an opaque building, the joint's visual properties are irrelevant. Concrete poured continuously across a connection conceals the joint beneath the surface material. Steel welded or bolted at connection points is covered by fire protection, then cladding, then interior finish. The joint exists structurally but is invisible architecturally, and the decision to make it invisible is effortless because opacity solves the problem without effort. In a transparent building, every joint is visible. The observer looking through the structural glazing toward the limestone wall sees, in the path of that sightline, every connecting element between every panel. A mechanical fastener at a glass panel joint, a steel bolt, a neoprene compression gasket, a clamping plate, reads as a dark interruption in the visual field. Multiply that interruption by the number of joints in a multi-tier transparent hyperrise and the building is not visually continuous. It is a grid of opaque connection points with transparent infill panels between them. The infill panels show you the cenote. The connection points show you the building. The observer's eye moves between these two registers constantly, and the experience is not of being inside a geological formation. It is of being inside a transparent cage. The joint specification for Pipe Dream's translucent structures: no mechanical fastener visible from the occupied interior or from the cenote water exterior. No gasket material occupying a visual plane intersecting the observer's sightline. No clamping plate, no bolt head, no compression fitting. The structural connection must be achieved through geometry, panel edges shaped to interlock mechanically without any added fastening hardware, and sealed with fast cure marine polymer applied at the joint interface that cures optically clear, cures chemically stronger than the adjacent panel material, and becomes, once cured, visually indistinguishable from the panel itself at any angle of observation. The joint is the strongest point in the assembly. This is not a consolation for making the joint complicated. It is the structural outcome of making the joint out of fast cure marine polymer that is stronger than the glass or polycarbonate panel it joins. When the structure approaches its load limit, it fails in the panel, the material the coordinating system's optical sensors are monitoring for crazing, not at the joint. The failure begins where it is visible. The joint holds after the panel has already told you it is in distress. The building's failure sequence is legible because the failure sequence was designed to start in the component with the most observable warning signature. The interlocking geometry is designed backward from 3 simultaneous constraints: the fast cure polymer's optimal joint width for full cure penetration, the maximum panel edge angle that can be achieved during aerial delivery and swarm-assisted alignment without applying force that risks panel fracture before the joint is sealed, and the minimum contact surface area required for the cured joint to achieve its strength specification. These 3 constraints, optimized simultaneously by the coordinating system's digital twin before the first panel is fabricated, produce a joint profile that appears in every panel edge across every depth tier, every material grade, every module in the network. One joint profile, universal application. The swarm units know one sealing sequence. The spare polymer cartridges carried in every maintenance sub are compatible with every joint in the installation. Standardization is not the enemy of elegance. It is what makes elegance maintainable at geological timescales. The delivery problem, vertical addition. The aerial delivery constraint that determined the founding module's jigsaw architecture does not change when construction turns upward. The heavy lift unit still operates through the cenote opening. Its payload limit still defines the maximum size of any single structural component. The swarm still handles positioning and sealing in the windows between heavy lift sorties. None of these parameters change because the construction direction has changed from horizontal to vertical. What changes is the assembly platform. When the founding module's first level was assembled, the water surface was the assembly platform, components were lowered to the water, floated into position, interconnected by the swarm. The water is passive and universal. It offers no preferential support to any component geometry, requires no preparation, and charges no rent. It is the ideal assembly platform for a floating structure. When the second tier is added above the first tier is the assembly platform. When the third tier is added above the second tier is the assembly platform. Each successfully completed level is simultaneously the terminus of the current phase and the construction deck for the next. The swarm, which floated during founding module assembly, now operates on a solid deck, the roof surface of the level below, with direct physical access to the assembly zone above it. This changes the swarm's operating parameters significantly. On water, the swarm's primary positioning challenge was drift, keeping a component stationary on a fluid surface while the joint was being seated and the polymer applied. On a solid deck, drift is not the problem. The problem is height. Each successive tier is assembled at a greater distance from the cenote opening through which the heavy lift unit is delivering components. At the founding tier, the delivery distance is short. At the fifth tier above founding level, assuming 3-meter floor-to-floor heights, the component is being lowered 15 meters through the cenote opening and then an additional 15 meters to the assembly deck below. 30 meters of tether, in a space where the cenote walls converge or expand unpredictably, where wind through the canopy opening introduces pendulum motion to the suspended load, where the swarm must intercept and stabilize the component before it contacts the assembly deck. The solution is two-stage delivery. The heavy lift unit lowers the component to a reception platform, a temporary staging structure assembled by the swarm at the cenote rim on the first construction day and disassembled when the cenote's final tier is complete. The reception platform receives the component from the heavy lift unit at canopy level, where tether length is short and pendulum motion is minimal. A secondary lowering system, lighter gauge, operated by swarm units anchored to the reception platform, takes the component from the reception platform down to the assembly deck at the controlled rate and orientation the joint sealing sequence requires. Two lowering systems in series rather than one long tether. The heavy lift unit is decoupled from the precision work at the assembly deck. The swarm manages both handoffs. The heavy lift unit's time in the airspace over the cenote is reduced to the minimum required for the primary lowering, increasing sortie frequency, reducing the construction window, compressing the schedule. The stacking protocol established in the founding sequence compounds across every tier added. Each level's trial window is shorter than the previous levels because each previous level has already asked the formation's primary stability questions and received answers. By the fifth tier, the formation's seasonal behavior is modeled at high confidence. The trial window has compressed from the founding level's minimum 12 months to a matter of weeks, enough time for the coordinating system to confirm that the new tier's ballast configuration is consistent with the existing model, not enough time to discover something the model does not already know. The civilization that spent the longest time listening at the beginning builds the fastest at every subsequent level. Patience purchased at founding is speed purchased in perpetuity. Thermal management in a transparent skin. Glass transmits solar radiation differently than opaque materials. An opaque wall absorbs incident solar energy at its outer surface, converts it to heat, and conducts that heat inward at a rate determined by the wall's thermal conductivity. The heat load on the interior is manageable because the opaque surface acts as a buffer, it absorbs before it transmits. A transparent wall transmits incident solar energy directly to whatever is behind it. The cenote water surface, struck by the light column through a transparent founding module roof, receives the full solar radiation load without buffering. For aquaculture, this is a managed input, photosynthetically active radiation for algae and plant species, a thermal input to the freshwater zone's temperature profile, a biological activity trigger for species tuned to natural light cycles. For the structural glazing itself, the thermal management challenge is differential expansion. Glass and polycarbonate have different coefficients of thermal expansion. A joint between dissimilar materials that heats and cools on the daily solar cycle will flex at the joint on every cycle. Repeated flexing at a rigid connection fails. Repeated flexing at a compliant connection is accommodated. The fast-cure marine polymers' post-cure mechanical properties include controlled compliance, not rigid, not elastomeric, but a modulus of elasticity calibrated to absorb the differential expansion between the two materials it joins without transmitting stress to either panel edge. The polymer joint is the expansion joint. No separate thermal break, no additional component, no secondary seal required. The joint geometry that achieves optical invisibility also achieves thermal accommodation because it was designed to do both simultaneously. The deeper thermal management problem is the halocline. Below the halocline, water temperature drops 8 to 12 degrees Celsius relative to the freshwater zone above. A transparent building crossing this boundary has structural elements simultaneously in warm water above and cold water below. The polycarbonate tube sections specified for halocline zone applications are selected in part for their thermal shock resistance. Polycarbonate absorbs thermal stress gradients that would fracture cast acrylic. But the joint at the halocline boundary, between a panel whose upper half is in warm freshwater and lower half is in cold saltwater, is in continuous thermal gradient. The polymer's compliance specification accounts for this. The coordinating system's structural health monitoring tracks thermal gradient measurements from the halocline zone tube wall sensors and compares them against the compliance model's predictions. Deviation from prediction triggers inspection, not alarm. The building is being listened to continuously. It is not being reacted to after the fact. The acoustic architecture. A cenote is not silent. Underground rivers running through limestone passages produce continuous low-frequency vibration transmitted through the rock and into the water at frequencies the human body registers as pressure rather than sound. The Chicxulub fracture network transmits distant geological events at frequencies below the threshold of hearing but above the threshold of structural resonance. Biological activity, the dolphin sonar systems in the freshwater zone, the ultrasonic maintenance cycling of the squeegee bots below the halocline, the acoustic cavitation of the lithocrustacean boring operations in the tunnel expansion galleries, fills the frequency spectrum from infrasound to ultrasound with continuous, managed, but not trivial acoustic energy. A transparent building is not acoustically neutral. Glass transmits vibration at different frequencies than polycarbonate. Polycarbonate transmits differently than the borosilicate carbon composite panels specified for the mid-depth horizontal transit arteries. The piezoelectric sensors embedded in the borosilicate carbon composite panels during fabrication, designed as a continuous structural health monitoring system, are also, by physics, acoustic sensors. They convert every pressure fluctuation in the composite into a data signal feeding the coordinating system. The structural monitoring system and the acoustic monitoring system are the same system, built into the same panels, reading the same physical events through the same physics. The coordinating system's acoustic management protocol schedules all ultrasonic maintenance activity, squeegee bot operations, lithocrustacean boring sessions, scavenger communications, against the biological and structural acoustic load at each depth zone, minimizing overlap between sources that would produce interference crosstalk. The dolphin sonar management layer is the most complex scheduling constraint. The dolphin's acoustic activity is not on a coordinating system managed schedule. It is on a dolphin schedule. The coordinating system does not suppress dolphin sonar. It schedules all managed acoustic activities around the observed dolphin activity pattern, treating the dolphin's acoustic sovereignty as a fixed parameter and adjusting everything else. For the building's structural vibration management, the relevant concern is resonance. Any structure has natural resonant frequencies, the frequencies at which applied vibration is amplified rather than damped. A resonance event at a structural frequency, driven by an underground river's characteristic vibration or a geological transmission from the Chicxulub fracture network, will amplify that vibration through the building's structural members until either the vibration source ceases or the structure fails. Standard engineering practice: calculate the natural frequencies of the structure, ensure the expected forcing frequencies are not among them, add damping if they are. In a transparent building, the damping layer cannot be opaque. Viscoelastic polymer damping sheets, the surface world standard for vibration management in glazed assemblies, are translucent but not optically clear. Applied at structural connections, they introduce the visual interruption the joint specification prohibits. The solution is in the fast-cure polymer's post-cure viscoelastic properties. The same polymer joint that achieves optical invisibility and thermal accommodation also achieves damping. The polymer's loss factor, its ability to convert mechanical vibration energy to heat through internal molecular friction, is specified alongside its optical clarity and thermal compliance. One material, engineered simultaneously for 3 performance requirements. No added component. No visual interruption. The joint is the damping layer because the joint's material was designed to be the damping layer from the specification phase. The structural resonance calculation, performed by the coordinating system's digital twin before any panel is fabricated, identifies the building's natural frequencies at every stage of assembly. Each tier added to the hyperise changes the structural system's mass and stiffness distribution, changing the natural frequencies. The coordinating system recalculates at every tier addition and confirms that the forcing frequencies observed in the formation data do not intersect the new frequency profile. If they do, the tier's geometry or ballast distribution is adjusted before construction begins. The building is never built into a resonance condition. The building's frequency profile is managed as an ongoing calculation, not a one-time design check. Biofouling is structural information. Every surface in a cenote that is not being actively maintained is being colonized. Bacteria arrive first. Within hours of a new surface being introduced, a conditioning film of organic molecules adsorbs to the substrate, and bacteria follow the conditioning film, anchoring with their own extracellular adhesive matrix and beginning to divide. Algae and biofilm-forming protists arrive within days, once the bacterial community has established the biochemical gradients they require. Within weeks, a new structural panel in the freshwater zone has a biofouling community in early succession. Within months, the community is mature enough to reduce optical transmission measurably. This is not a contamination problem. It is a calibration opportunity. The coordinating system's optical transmission sensors, monitoring every tube section and structural panel at 8-hour intervals, record the transmission coefficient continuously. The rate of transmission decline over time is the biofouling rate at that location. The biofouling rate is a function of depth, water chemistry, biological community density in the surrounding water column, proximity to nutrient sources, temperature, and the particular surface chemistry of the panel material. The map of biofouling rates across the full panel inventory is, simultaneously, a map of these variables across the cenote's full three-dimensional volume. The Ancestris Vitreous Colony Management Protocol uses this map directly. The coordinating system allocates cleaning school deployments based on the optical transmission gradient across the panel inventory. Highest fouling rate zones receive highest cleaning priority. The acoustic transponder network that steers the cleaning schools toward high priority zones is sending the fish where the transmission data says they are needed. The fish are not operating on a schedule. They are operating on a continuously updated demand signal generated from the building's own self-reporting. Below the halocline, where Ancestris vitreous cannot survive, the SqueegeeBot fleet covers the same function. The same optical transmission data drives the same priority allocation. The coordinating system does not distinguish between biological and mechanical maintenance capacity in its allocation algorithm. It manages cleaning coverage as a single resource pool deployed against a single demand surface, regardless of what the cleaning unit is made of. The biofouling map is also an early warning system for water chemistry anomalies. If the fouling rate at a cluster of panels increases sharply relative to the surrounding panels, the coordinating system flags it as a potential local chemistry deviation, nutrient intrusion, biological die-off releasing dissolved organics, limestone dissolution pulse, and dispatches a water chemistry sampling unit before the deviation propagates. The building is telling the coordinating system where to look. Structural monitoring, biological management, and environmental chemistry surveillance are not three separate systems. They are three interpretations of the same continuously generated optical transmission dataset. The building knows where it is being eaten. It reports this in real time. The coordinating system decides what to do about it. Construction without interruption. The stacking protocol structural logic, each completed level is the assembly platform for the next, implies a construction sequence in which the lower levels are occupied while the upper levels are being assembled. This is not an assumption. It is a design requirement. A civilization that halts habitation at lower tiers while constructing upper tiers has a construction schedule problem. The economics of the longevity program, the tourism operations, the research database, all of these depend on continuous occupancy. Evacuation of lower tiers for upper tier construction is not a schedule inconvenience. It is a civilizational revenue event with compounding effects on the expansion reserve. The assembly sequence for each new tier is designed to produce zero acoustic, vibration, or access interruption to the tier immediately below. The heavy lift delivery window is timed to the early morning hours when tourist guest traffic through the cenote is lowest and the biological acoustic management schedule has the least competing demand. Swarm operations on the assembly deck, the roof of the occupied tier below, are conducted through a vibration isolation interface. The swarm units operating on the assembly deck are fitted with compliant foot pads during construction mode, reducing transmitted vibration to below the threshold detectable in the occupied space below. The Fast Cure Polymers application at joint interfaces produces negligible vibration. The panel interlocking sequence produces a single acoustic event per joint, a low-magnitude click as the geometric interlock seats, that the coordinating system's acoustic monitoring confirms is below the threshold of structural concern and below the threshold of guest awareness. The guests in the longevity galleries below the construction deck are not told construction is happening above them. This is not deception. The acoustic signature of the construction operation is below the threshold of their sensory perception. Informing them would introduce an expectation of disturbance that the construction operation itself does not produce. The coordinating system monitors guest biometric data, heart rate, sleep quality, cortisol proxy measurements from the longevity program's continuous health monitoring through the construction period and confirms no deviation from baseline. The data is the evidence that the construction sequence is working. The absence of guest complaint is the evidence that the data is accurate. The civilization builds upward while it lives inside itself. This is not a construction achievement. It is the founding condition of any civilization that intends to keep expanding. The building at night. Daylight passes through the building. The building transmits it, refracts it, distributes it downward through its own transparent structure. At the closing of the light column, the moment when the sun's angle relative to the cenote opening no longer delivers direct illumination to the water surface, the building transitions from passive light transmitter to active light source. The light cannon relay arrays, mounted at the surface tier where the daylight column is strongest during operating hours, redirect their diodes from downward transmission mode to full cenote illumination mode. The laser arrays trace the tube network outward from the surface tier into every horizontal corridor and vertical gallery. Total internal reflection transmits the light through kilometers of tube at an intensity sufficient to illuminate the aquaculture galleries, the transit corridors, the structural column forests of the hyperrise interior, the cave walls beyond the building's perimeter. From inside the building at night, looking outward through the transparent walls, the limestone formations are illuminated by light that originated inside the building and is now outside it, having passed through the transparent structure as through air. The stalactites are lit by the building. The cave walls are lit by the building. The water column between the building's exterior panels and the cenote wall, the space that is neither inside the building nor inside the unmodified cave, is illuminated by both, and the light from these two sources meets in that intermediate space and produces a visual field that has no category in surface world architectural experience. From outside, from a pedal submarine at halocline depth, looking upward through the blurry optical discontinuity of the halocline boundary at the lit hyperrise above, the building is a coherent luminous form suspended in darkness. Its geometry is fully legible. Its material is invisible. The observer sees light organized into a building-shaped volume, not a building containing lights. The structure and the illumination are the same object. This is the aesthetic thesis of the translucent revolution stated in engineering terms. The building achieves optical continuity with its environment during the day by transmitting the environment's own light through its structure, and achieves luminous presence at night by becoming the source of the light that reveals the environment. In neither state is the building visually separable from what it occupies. In neither state is the cenote visually separable from what it contains. A building that cannot be seen except as the environment that contains it has achieved the engineering specification that aquaforming doctrine requires. Not because it has made itself small or modest or deferential to the geological context, the hyperrise is a large structure by any physical measure. But because it has organized itself according to the formation's own visual logic rather than importing a visual logic from outside. The cenote, at night, illuminated from within by the civilization it contains, looks like a cenote that has learned to generate its own light. Not like a cenote that has been occupied by something that generates light. The distinction is the difference between aquaforming and everything that preceded it. Cross-references, Part 2, CH1, Cities Made of Light, Part 2, CH3, Materials That Let Civilization Disappear, Part 4, CH2, Autonomous Construction, Part 5, CH1, Cleaner Fish, Part 7, CH1, Breakaway Architecture. For Joint Polymer Specification and Load Testing Protocol, see Appendix C, Materials Certification Record. For Acoustic Scheduling Parameters and Dolphin Sonar Management Protocol, see Appendix F, Biological Operations Manual. Chapter 3, Materials That Let Civilization Disappear. Disappearance is not one thing. A material can disappear optically, transmitting light rather than absorbing or reflecting it, without disappearing chemically, without disappearing mechanically, without disappearing biologically. A material can be optically clear and chemically reactive, dissolving in the cenote's mineral-saturated water while showing you perfect views of the dissolution. A material can be optically clear and biologically attractive, colonized to opacity within weeks by the fouling community regardless of what its factory datasheet says about light transmission. A material can be optically clear and mechanically wrong, appropriate refractive index, catastrophic failure mode. The engineering specification for a material that lets civilization disappear inside a cenote is not a single specification. It is 4 simultaneous specifications that must be satisfied simultaneously, at the specific depth at which the material will operate, across the specific chemical and biological conditions of that depth, across the full design life of the installation. A material that satisfies 3 of the 4 specifications has not satisfied the specification. It has identified itself as unsuitable for a different reason than expected. The full matrix has 5 entries. No single entry satisfies all conditions at all depths. Each entry governs a depth zone. The transitions between zones are the most demanding engineering problems in the building's material architecture, because at the transition boundary 2 materials with different properties, different thermal expansion coefficients, different moduli of elasticity, different refractive indices, different biofouling susceptibility profiles, must meet at a joint and produce, at that meeting point, the same optical continuity that each material produces alone in its own zone. The joint is always the hardest problem. The material is never the hardest problem. The materials are known. The physics of each material in its zone is calculable. The joint between dissimilar materials at a zone boundary, in conditions that differ on either side of the boundary, in a space that the coordinating system has modeled but the formation has not finished describing, this is where the specification concentrates its demands. Zone 1, the surface and the shallow freshwater column. Cast PMMA, polymethyl methacrylate, acrylic in its architectural form, is the material of first encounter. Every guest arriving at the founding module steps onto or through a surface tier built from acrylic. Every orientation gallery, every check-in corridor, every rim-level observation platform is bounded by material that transmits light at a refractive index close enough to waters owned at the boundary between them, at low-angle observation, approaches invisibility. This property is not cosmetic. The refractive index match between PMMA and water means that light arriving at the material boundary from the water side is refracted minimally. The familiar bending of light at a glass-water interface that makes submerged objects appear displaced is reduced to a degree that experienced cenote divers describe as uncanny. The material is there. The physics confirms it. The eye does not process it as a boundary between 2 different media. The eye processes it as a continuation of the water column with something organized inside it. The surface tier operates in UV-exposed conditions. The light column delivers the full solar spectrum including the near-UV radiation that conventional acrylic cannot withstand without yellowing. UV stabilization packages available in high-quality PMMA formulations prevent chain scission in the polymer backbone at UV wavelengths that would otherwise initiate the yellowing process over months to years of continuous exposure. The stabilized formulation maintains optical clarity across the design life. The unstabilized formulation does not. The procurement specification for all surface tier PMMA includes UV stabilizer content as a mandatory test parameter, not a manufacturer's claim. Incoming panels are tested before installation. Panels that do not meet the UV stabilizer threshold are returned. The Cenotes light column will test every panel continuously from the day of installation. The procurement protocol tests it first. The failure mode of acrylic under impact is the material's principal engineering liability at the surface tier. PMMA is brittle in the mechanical sense, it does not deform plastically before fracture. Applied impact energy produces a crack that propagates at high velocity across the panel, producing catastrophic failure rather than the gradual visible distress of crazing in aluminosilicate glass. Surface tier panels are exposed to the impact hazard most likely to be encountered in the cenote environment: falling equipment from aerial delivery operations, guest activity in the orientation galleries, biological debris from the jungle canopy above the cenote opening. The impact protocol addresses this by layering rather than by material substitution. A thin polycarbonate sacrificial layer, 8 mm, bonded to the acrylic's exterior face with optically clear adhesive, absorbs the impact energy that the acrylic itself cannot deform to accommodate. The polycarbonate layer cracks under impact, locally and visibly, without transferring the fracture energy to the structural acrylic behind it. The sacrificial layer is replaced. The structural panel is untouched. Two materials doing one job is not a design failure. It is the recognition that no single material satisfies both the refractive index requirement and the impact resistance requirement at the surface tier, and that the zone's conditions require both. The surface world response to this recognition is to develop a new material that does both. Pipedream's response is to use two existing materials each doing what it actually does well, and to make their junction, the optically clear adhesive bond, the technical achievement rather than the material itself. Biofouling rate at the surface tier is the highest in the installation. Maximum incident light, maximum nutrient loading from the jungle canopy's organic inputs, maximum biological activity in the warm freshwater zone. The Ancestris vitreous cleaning colonies are deployed in highest density here. The optical transmission sensor network samples this zone at the shortest intervals of any zone in the installation, 4 hours, rather than the 8-hour standard for deeper zones, because the fouling rate makes 4-hour sampling the appropriate resolution to catch transmission decline before it compounds. The surface tier is the zone with the least geological distance from the surface world. It is also the zone with the most rapid biological colonization, the highest UV load, the most frequent human contact, the most demanding impact environment. It is the most fragile tier by every operational metric. It is also the most replaceable. Panels at the surface tier can be swapped by the build swarm operating in standard mode, without pressure suits, without access restrictions, in daylight, with standard tooling. The design life expectation for a surface tier PMMA panel is shorter than for any other material in the matrix, and the replacement schedule is more frequent, and this is not a liability. A material specified to its actual conditions with a replacement schedule matched to its actual service life is correct engineering. A material specified to exceed its actual conditions in order to achieve a longer replacement interval that still underperforms the material's own design life is expensive engineering that defers the same outcome. Zone 2, the halocline transition. Polycarbonate, heavy wall, engineered formulation, governs the halocline zone and the mid-freshwater column below the surface tier's UV exposure band. The specification transition from PMMA to polycarbonate at roughly 8 meters depth reflects the point at which the UV exposure calculation drops below the threshold where PMMA's yellowing risk is a material concern, and where the halocline's thermal gradient becomes the dominant material challenge. Polycarbonate's impact resistance is the fact that defined its surface world identity, 250 times the impact resistance of standard glass, the material of riot shields and aircraft canopy glazing. In the cenote context, this property matters less at the halocline zone than it does at the surface tier, because the impact hazard profile diminishes with depth. Below the zone of direct aerial delivery operations and guest boarding activity, the impact sources are smaller and slower: maintenance equipment, biological matter in suspension, the occasional sub-positioning error at a docking port. Polycarbonate was not selected for the halocline zone because of its impact resistance. It was selected because of its thermal behavior. The halocline's temperature gradient, 8 to 12 degrees Celsius across a vertical span of 15 meters, imposes a thermal cycling load on any structural panel crossing it. A panel whose upper meter is in water at 28 degrees Celsius and whose lower meter is in water at 17 degrees Celsius is not a panel at a uniform temperature. It is a panel with a temperature gradient inscribed across its material. That gradient produces differential thermal expansion within the single panel, The warm upper portion wants to be slightly larger than it is at the cool lower temperature, the cool lower portion wants to be slightly smaller than it is at the warm upper temperature, and the two portions are the same solid object, so neither can be what it wants to be independently. The result is internal stress, thermal stress, distributed across the panel in a pattern determined by the temperature gradient profile and the material's coefficient of thermal expansion. Cast acrylic's coefficient of thermal expansion is higher than polycarbonate's. An acrylic panel spanning the halocline gradient would accumulate more internal thermal stress per degree of gradient than a polycarbonate panel of identical dimensions. Over the daily thermal cycling the halocline gradient imposes, the gradient varies with surface conditions, with rainfall, with seasonal shifts in the freshwater recharge rate from the jungle above. The acrylic panel would accumulate fatigue damage at a rate that the polycarbonate panel does not. The halocline is not a static boundary. It is a dynamic zone that breathes with the weather, the seasons, and the annual rainfall cycle. Any material specified for the halocline zone is specified for a boundary that will move, repeatedly, across the material's own thickness, cycling the thermal gradient through the panel on a schedule the coordinating system can model but not control. Polycarbonate's lower coefficient of thermal expansion and higher ductility, its ability to deform slightly under load rather than accumulating internal stress, make it appropriate for this environment in a way acrylic is not. Its optical properties are the trade. Polycarbonate yellows under sustained UV exposure at a rate acrylic's UV stabilizer packages have been formulated to resist. Below the surface tier's UV band, polycarbonate yellowing is not a design life concern. The material makes its compromise with the zone's conditions and the zone's conditions make their compromise with the material, and the result is a match that acrylic cannot achieve at the halocline and polycarbonate cannot achieve at the surface tier. The halocline's visual properties, the optical dissolution, the gelatinous blurring, the light behaving as though it has abandoned its own rules, pass through the polycarbonate panel without being interpreted by the panel. The panel does not know it is showing the observer something unusual. It is transmitting the light that arrives at its surface with the fidelity its optical clarity specification requires. The unusual thing the observer is seeing is the cenote. The panel is the medium. The cenote is the message. Zone 3, the structural depth. Chemically strengthened aluminosilicate glass, the column material whose crazing failure signature was established in Chapter 1, extends from approximately 50 meters depth to the lower boundary of the aerobic zone. This is the structural workhorse of the hyperrise system, the material that carries the civilization's lateral loads through hoop stress in the building's circular cross-section, that displays its own distress before failing, that achieves its performance through the chemistry of its surface rather than through added reinforcement or composite structure. The strengthening process is not a coating. It is an exchange, sodium ions at the glass surface replaced by larger potassium ions in a hot potassium nitrate salt bath. The exchange happens at the surface of the glass object after it has been shaped to final geometry. No subsequent cutting, grinding, or edge work is permissible after strengthening. Any action that removes material from the strengthened surface removes the compressive stress layer with it, and the panel's structural properties revert locally to those of the unstrengthened glass. The strengthening process is the last manufacturing step. The panel that enters the salt bath is the panel that is installed. This has a procurement implication that governs the entire deep zone construction sequence. Every panel in the aluminosilicate glass inventory must be manufactured to final geometry before strengthening, without any adjustment to be made after strengthening, without any field modification of any kind. The coordinating system's digital twin of the installation must be accurate to the tolerance the glass manufacturer achieves at the strengthening step, typically plus or minus 1 mm on edge dimensions, because the field cannot correct a dimension error by trimming the panel. A panel with a dimension error discovered after strengthening is a panel that must be returned to the manufacturer, a replacement fabricated and strengthened, and the construction sequence for that gallery section delayed until the replacement arrives. The quality control protocol for aluminosilicate glass panels is therefore front-loaded more heavily than for any other material in the matrix. The coordinating system's digital twin generates cutting lists from the installation geometry at high precision. The manufacturer receives cutting lists, not general specifications. Each panel is matched to a specific location in the installation plan by identifier assigned at fabrication. The receiving inspection at the cenote confirms identifier, dimension, optical quality, and edge condition before any panel is transferred to the aerial delivery queue. A panel that fails receiving inspection is failed at the cenote rim, not after it has been lowered into the cenote, not after the swarm has begun positioning it for joint seating. At depth, in the halocline and below, the panel's refractive index, 1.52 for aluminosilicate glass, compared to 1.33 for water, produces a more visible optical interface than the PMMA's near match in the surface tier. The glass panel does not disappear into the water in the way the acrylic panel approaches invisibility. It is present as a boundary. The observer looking through it sees, at the boundary, the slight refraction of the image behind it that glass always introduces. At depth, in low light conditions, with the reduced visual acuity that comes from operating in a water environment through a scavenger visor, this optical presence is less noticeable than it would be in a fully lit surface inspection. But it is there. The glass does not pretend otherwise. The engineering decision to use aluminosilicate glass at these depths despite its optical presence is a decision made on the basis of what the depth zone's demands actually are: structural capacity, surface hardness against slow abrasion, resistance to the silicate mineral precipitation that occurs as deep cenote water slowly deposits dissolved limestone on every surface it contacts. In the surface tier, disappearance was the dominant requirement and structural demand was modest. At structural depth, structural capacity is the dominant requirement and optical perfection is secondary. The material selection reflects this honestly. A civilization built on first principles does not use the wrong material in the right way. It uses the right material where its actual performance profile matches the zone's actual demands. Zone 4, the anoxic boundary. Alone, aluminum oxynitride ceramic, the hardest optically transparent material in the installation, governs the anoxic zone and all structures in contact with the hydrogen sulfide environment of the chemostat layer. Its Mohs hardness of 9 places it at sapphire equivalence. Its optical transmission extends across the visible spectrum, the near UV range, and the mid-wave infrared, a spectral range that includes the wavelengths at which the deep galleries monitoring systems operate, the wavelengths at which the extremophile microbial communities emit bioluminescent signals that the coordinating system's biological census tracks, and the wavelengths at which hydrogen sulfide concentration is detectable by optical spectroscopy. The last property is not incidental. Alone panels in the anoxic zone are simultaneously the structural enclosure and the chemical monitoring interface. The coordinating system spectroscopic sensors, mounted inside the inhabited gallery looking outward through the alone panels into the chemostat zone, monitor hydrogen sulfide concentration in real time through the panel's midwave infrared transmission. The panel is the window and the instrument. The alone's transmission spec was not selected because it is optically clear in a general sense. Polycarbonate is optically clear in a general sense. It was selected because it is optically clear at the specific wavelengths the H2S monitoring requires, and simultaneously chemically immune to the H2S environment that would attack every other material in the matrix. Polycarbonate yellows under UV. Acrylic crazes under H2S attack. Aluminosilicate glass, though chemically resistant, is vulnerable to thermal shock at the temperature discontinuities the chemostat zone's bacterial metabolism introduces locally around active sulfide oxidizing vent communities. Alone does not react with H2S. It does not absorb UV to the degree that produces photodegradation. It is immune to thermal shock at the temperature differentials present in the anoxic zone. Its failure mode, catastrophic shear without the preceding observable crazing that glass provides, is the one liability the installation manages through redundancy rather than through material behavior. The alone gallery sections are the installation's most heavily monitored. The piezoelectric sensor arrays in the surrounding composite structure sampling structural condition at the highest frequency in the installation, precisely because the material does not warn before it fails. The fabrication of alone panels is the most technically demanding procurement task in the entire installation. Alone is not a glass, it is not formed from a melt poured or blown into shape. It is sintered from powder under high pressure and temperature, then densified in a proprietary process. The final form is a polycrystalline ceramic with optical transmission properties that emerge from the nanoscale grain structure achieved during sintering. Panel size is constrained by the sintering equipment's chamber dimensions. Large panels are not available from any source. The anoxic zone's module geometry is designed around the maximum alone panel size achievable from the manufacturing process, not the other way around. The available panel is the design constraint. The aerial delivery protocol for alone panels differs from the protocol for all other materials. Alone's failure mode, catastrophic shear without warning, means that any impact event during delivery that would be absorbed by polycarbonate and survived by glass might shatter an alone panel without visible precursor damage. The delivery protocol specifies, individual alone panels are packaged in custom-formed foam cradles designed to the panel geometry. Each cradle is a single-use item. The cradle that delivers one panel is not reused for another. The heavy lift unit carries no more than 2 panels per sortie to reduce the consequence of any single delivery incident. The swarm's panel handling sequence for alone includes impact sensors on the manipulator surfaces, set to abort any handling sequence that registers an impact event above the calculated threshold for safe panel handling. The panel that has experienced an impact event is quarantined, removed from the installation sequence and inspected before any decision is made about its suitability. No alone panel is installed without passing the incoming inspection at the cenote rim and a post-delivery inspection after the swarm transfer. 2 inspections, mandatory, no exception. The logic is simple: alone is the most expensive material in the installation and the one with the least observable damage signature. The inspections cost time. The cost of installing a damaged alone panel that fails in the anoxic zone, breaching the inhabited gallery into the H2S environment, is a cost the civilization does not calculate on a cost-benefit basis. It does not occur. Zone 5, the mid-depth artery. Borosilicate carbon composite, the mid-depth horizontal transit artery material, does not fit cleanly into the depth zone logic governing the other 4 materials. It appears at depths spanning the halocline zone and the shallow structural zone, not because the conditions in those zones require it rather than polycarbonate or aluminosilicate glass, but because the transit artery function requires something neither of those materials provides: embedded sensing. The piezoelectric sensors embedded in the borosilicate carbon composite panels during fabrication are not added to the panel after it is made. They are part of the panel. The carbon fraction of the composite matrix is not structural reinforcement alone, it is the conductive pathway network through which the piezoelectric sensors transmit their signals to the data bus running along the artery's interior. The panel and the sensor network are one object. The composites fabrication process is also the sensor installation process. This integration is the result of a manufacturing decision that has no precedent in surface world construction practice. Surface world structural panels are fabricated as structural objects. Sensors are added to them later, bonded to the surface, embedded in adhesive overlays, attached with mechanical clips. The sensor is always an addition to the panel, and the bond between the sensor and the panel is always the weakest element in the monitoring system. In humid environments, in cyclic temperature conditions, in chemically active water, sensor bonds fail before sensors fail. The data gap from a detached sensor is not the same as the data gap from a failed sensor. It has no observable signature and cannot be distinguished from a zone with no anomaly to report. The borosilicate carbon composites fabrication process eliminates the bond problem by eliminating the bond. The piezoelectric elements are placed in the layup before the matrix is infused. The matrix infuses around them during cure. The cured composite encapsulates the sensors in the same material matrix that constitutes the panel's structure. The sensor does not bond to the panel. The sensor is inside the panel. It fails only when the panel fails. Its data gap is the panel's failure signature. The result is a transit artery that is simultaneously a structural enclosure, a continuous acoustic sensor array, a vibration monitoring network, and the coordinating system's primary subhalocline data collection infrastructure. The tube that guides the cycle sub from the surface tier toward the deep galleries is also the tube that tells the coordinating system whether anything in the formation's acoustic signature has changed since the last sampling interval. The guest who pedals through it on a standard tourism route is inside the civilization's primary sense organ. The composite's optical properties are the compromise the material makes for its sensing function. Borosilicate carbon composite is not as optically clear as PMMA, not as thermally accommodating as polycarbonate, not as hard as aluminosilicate glass. It is optically translucent rather than optically transparent. The carbon fraction, even in the low concentrations that constitute the conductive network, introduces a slight opacity that reduces total light transmission relative to the purely transparent materials. The guest inside the transit artery can see the cenote through the tube walls clearly enough to understand what they are inside. The visual experience is not the same as looking through an acrylic surface tier panel. It was not designed to be. The transit artery's design hierarchy places structural integrity and sensing integration above optical clarity, because the artery's function, transit and monitoring, requires those properties more than it requires the visual perfection appropriate to an observation gallery. Disappearance, at the artery, means something different than disappearance at the surface tier. The material does not attempt invisibility. It attempts legibility, the formation visible through it, the civilization's monitoring function embedded within it, the transit function running through it, all three simultaneously present to the observer in a single structural object. A material that tries to disappear while performing three functions and succeeding at all three has earned its presence in the zone it occupies. The transition zones. 5 materials. For transition boundaries where dissimilar materials meet at zone edges. Each boundary is the most mechanically and optically demanding location in its vicinity. The PMMA to polycarbonate transition at approximately 8 meters depth is the most optically sensitive. The refractive index difference between the two materials, 1.49 for PMMA, 1.586 for polycarbonate, produces a boundary reflection at the joint interface that is visible under direct lighting. Light arriving at the interface from the PMMA side encounters a medium of higher refractive index and reflects a fraction of its energy backward. The reflected fraction is small. Fresnel reflection at this index difference is approximately 0.2%, but in a structure whose optical design objective is invisibility, 0.2% reflection at a structural joint is a visible artifact. The observer looking at the joint from the right angle in the right light sees a faint brightness at the transition that reveals the material boundary. The mitigation is index matching adhesive, an optically clear adhesive formulated to a refractive index between the two materials, applied in a thin layer at the joint interface, reducing the index step at each interface by half and reducing the Fresnel reflection accordingly. The adhesive does not eliminate the optical artifact. It reduces it below the threshold of detectability under the cenote's ambient lighting conditions at the transition depth. In direct high-intensity illumination, in the maintenance inspection lighting conditions used when the coordinating system's optical sensors flag an anomaly at the transition zone, the artifact is detectable by the inspection protocol. It is not detectable by a guest on a standard transit route in ambient light. The polycarbonate to aluminosilicate glass transition at structural depth is primarily a thermal management problem. Polycarbonate's thermal expansion coefficient is approximately 3 times that of aluminosilicate glass. A temperature change of 20 degrees Celsius, within the cenote seasonal range, produces dimensional change in the polycarbonate element 3 times larger than in the glass element. At the joint between them, this differential produces shear stress in the fast-cure polymer joint. The polymer specified loss factor, its viscoelastic damping property, serves double duty here. It absorbs thermal differential expansion in the same mechanism by which it absorbs acoustic vibration. The joint is not designed for one type of stress accommodation. It is designed for the stress accommodation function, and thermal differential expansion and acoustic vibration are 2 instances of the same physical phenomenon, relative displacement between 2 bonded solid bodies that the bonding medium must accommodate without transmitting the displacement to either body as damage. The aluminosilicate glass to alone transition at the anoxic boundary carries the highest chemical risk of any transition in the installation. The anoxic zone's hydrogen sulfide environment is in direct contact with the exterior surfaces of panels on both sides of the transition. The glass is not attacked by H2S. The alone is not attacked by H2S. The fast-cure polymer joint between them, specified for optical clarity, thermal accommodation, and acoustic damping across the rest of the installation, is the liability. The polymer formulation used at the anoxic boundary transition is a modified version of the standard formula, with the H2S-resistant additive package that increases chemical resistance at a cost of slight reduction in optical clarity. At the anoxic boundary, the joint between 2 highly optically clear materials is slightly less clear than either material. The coordinating system's optical sensors are calibrated to this expected transmission reduction at the anoxic boundary joints, and flag deviations above the expected value rather than deviations from full transparency. Every transition zone is documented in the coordinating system's installation record with its specific optical, thermal, chemical, and mechanical properties, the actual properties of the installed joint, measured after installation, not the design specification properties. The record is the formation's honest assessment of where the installation met its own specification and where it did not. Every deviation from specification is a data point. Every data point refines the digital twin. Every refined digital twin improves the next installation. The civilization improves by knowing where it fell short. It maintains the record of its shortfalls not as a defect register but as a learning database. The material that let civilization disappear also lets civilization see itself. The material record. The founding civilizations of the surface world built their infrastructure from materials that aged visibly: wood rotted, iron rusted, limestone eroded, concrete cracked. The deterioration of the material was the record of the time the infrastructure had been in service. An archaeologist examining a stone building could read the stone's surface condition, the depth of weathering, the biological colonization pattern, and reconstruct the building's age and service history with reasonable confidence. Pipe Dream's translucent infrastructure ages differently. Acrylic transmits less light as UV stabilizers are exhausted. Polycarbonate accumulates micro-scratches on surfaces the squeegee bots have cleaned 10,000 times. Aluminosilicate glass columns develop faint crazing in the zones where lateral loads have been highest over the installation's life. Alone panels at the anoxic boundary show mineral precipitation patterns where the chemostat zone's dissolved mineral output has contacted their surfaces and deposited. Borosilicate carbon composite arteries carry the acoustic record of every geological event the formation has transmitted through the installation since the first tube section was sealed. None of these aging signatures are visible to the unaided eye at normal observation distance. All of them are visible to the coordinating system's sensor network, continuously, in real time. The digital twin carries the material record of every panel in the installation, not as a theoretical projection from initial conditions but as a continuously updated actual record derived from sensor readings. The material record is the civilization's memory. Not of events, those are in the governance archive, the biological census, the research database. Of what the formation asked of the structure and what the structure gave in return. The panel that has been cleaned most frequently is the panel in the highest biological activity zone. The panel that has accumulated the most crazing is the panel in the highest lateral load zone. The panel that required the earliest replacement is the panel in the conditions the design specification underestimated. Every replacement is a calibration. The coordinating system records the service life achieved, compares it to the modeled prediction, updates the prediction for all panels in similar conditions, and adjusts the maintenance schedule forward. The civilization does not repeat a material failure. It integrates the failure into the model and manages against the updated model. A civilization that builds from materials it can see through also builds in materials that it can learn from. The transparency is not only optical. It is institutional. The formation can be read through the structure because the structure was built to let it be read. This is why the material specification begins with disappearance and ends with legibility. Not because these are different goals. Because they are the same goal stated from opposite directions. Cross-references, Part 2, CH1, Cities Made of Light, Part 2, CH2, Engineering Invisible Architecture, Part 2, CH4, The Crystal Tube Standard, Part 4, CH2, Autonomous Construction, Part 7, CH4, Living Through Failure. For full material property specifications and third-party certification records, see Appendix C, Material Certification Record. For a loan panel delivery protocol and inspection checklist, see Appendix D, Construction Operations Manual. Chapter 4, The Crystal Tube Standard. The founding module is not a civilization. It is a proof. The proof establishes that permanent occupation of a cenote is achievable at this depth, in this formation, under these geological conditions. It establishes nothing about the second cenote, or the third, or the corridor passage connecting them. A civilization is not a habitation unit. It is a network of habitation units connected in ways that allow what one unit produces to become what another unit uses: energy, food, water, people, information, governance authority. Without the connections, the civilization is a collection of experiments. With the connections, it is a body. The Crystal Tube Standard is the specification for the connections. Every tube section in the Pipe Dream network, from the founding module's first horizontal gallery to the deepest transit artery in the anoxic zone's outer perimeter, from the kilometer-long corridor passages linking formation cenote to corridor cenote to the meter-scale stub tubes connecting adjacent habitation modules within a single tier, is fabricated and installed to the Crystal Tube Standard. 1 Standard. Universal application. The standard does not describe a tube material or a tube geometry. It describes a tube function, what every tube in the network must simultaneously be, must simultaneously carry, and must simultaneously survive. A tube that meets the Crystal Tube Standard is not a transit corridor with utilities sharing the space. It is a single structural object performing transit, utility, sensing, illumination, and safety functions simultaneously, in the same cross-sectional area, without any function degrading any other function's performance below the specification threshold for that function. The functions are not sharing the tube. They are constituting it. Remove any one function and the remaining object is not a crystal tube. It is a component. The civilization is built from crystal tubes. Components are not the civilization. Why a standard? The surface world builds infrastructure through specialization. A water pipe is a water pipe. A transit corridor is a transit corridor. A data cable is a data cable. Each is designed for its function alone, installed by a trade that knows that function alone, maintained by a specialist who is not the specialist who maintains the adjacent pipe performing the adjacent function. The fragmentation of function into specialized infrastructure produces infrastructure that is efficient at its individual function and expensive at its aggregate cost. The cenote that contains a transit corridor, a water main, a data cable run, a power conduit, a drainage pipe, and a lighting system contains 6 objects where one was needed, requires 6 installation sequences where one was available, and fails in 6 different ways that 6 different maintenance regimes must detect and address. The aerial delivery constraint eliminates this option before it becomes a temptation. Every component delivered to a cenote installation arrives through a canopy opening that offers no loading dock, no crane platform, no simultaneous delivery of multiple large objects. The heavy lift unit delivers one primary structural component per sortie. The construction window available between sorties is finite. The swarm's assembly capacity within that window is finite. A construction strategy that requires 6 installation passes for 6 specialized pipe types, in a space where each installation pass consumes the same finite construction window, is a strategy that extends the construction timeline by a factor of 6 relative to a strategy that installs one multifunction object in one pass. The Crystal Tube Standard is what a multifunction object looks like when the function list is derived from what a civilization actually needs its connections to do, not from what existing engineering disciplines know how to build. There is a second reason for the standard that the cost argument does not capture. A network built from a single standardized component has 1 failure mode. A network built from 6 specialized components has 6 failure modes, and the interactions between adjacent components introduce failure modes at interfaces that are not the failure mode of any individual component. The Crystal Tube's failure modes are known, documented, predicted by the coordinating system's digital twin, and managed by maintenance protocols written for one component type. When the tube fails, the failure manifests in one of the ways the standard has identified, within the range of parameters the standard has bounded, and is addressed by the maintenance protocol the standard specifies. The coordinating system does not need to determine which of 6 specialized systems has failed and refer the failure to the appropriate specialist trade. It identifies a crystal tube condition event and dispatches the crystal tube maintenance response. Standardization is not the elimination of complexity. It is the relocation of complexity from the maintenance phase, where it is expensive and dangerous, to the specification phase, where it is the engineering team's problem rather than the formation's. The geometry. The crystal tube's cross-section is circular. The formation determined this before any engineer made a recommendation. Cenote passage geometries produced by water-dissolving limestone are not rectangular. They are not the right-angled spaces that surface world construction has organized itself to fill. They are the shapes that water makes when it exploits fracture networks and bedding planes and zones of differential limestone solubility, ovoid, kidney-shaped, lenticular, occasionally approaching circular where dissolution has proceeded uniformly in all directions from a central void. The lithocrustation boring operations that expand existing passages and create new ones produce circular bores by default, because the boring swarm operates radially from a central axis, each unit maintaining equal distance from that axis by acoustic coordination with its neighbors. The bore is circular because the swarm is symmetrical. A circular tube and a circular bore is the most natural fit the installation can achieve. The annular space between tube exterior and bore wall is uniform around the circumference, giving the lithocrustation colony that lines the bore wall with calcium carbonate paste an equal surface to maintain on all sides. The anchor points securing the tube to the bore wall are equally spaced around the circumference, distributing lateral load symmetrically. No weak axis. No load concentrating corner. The circular section in a lateral load environment performs identically to the circular column in the hyperise. Hoop stress distribution eliminates preferential failure directions. The circular cross-section also determines the tube's internal zoning. The interior of the crystal tube is not a single undivided space. It is a cross-section organized into concentric and segmented zones, each carrying its assigned function, none interfering with any other. The transit zone occupies the central axis, the largest single region of the cross-section, sized to accommodate the cycle sub or maglev pod geometry with clearance margins for passenger egress, maintenance access, and the fluid pressure management that pod movement through an enclosed tube requires. The guide rail runs along the bottom of the transit zone, fixed to the tube's structural inner surface at standard intervals. The maglev induction track is integrated into the guide rail. The rail is the track, not a separate component mounted on a separate structure. One installation operation seats both the mechanical guidance function and the electromagnetic propulsion function. The utility zone occupies the annular space between the transit zone's outer boundary and the tube's structural wall. It is divided into quadrants by thin polymer divider panels, transparent, continuous with the tube wall's optical properties, providing physical separation between utility runs without visual interruption of the cenote view. The utility quadrants carry, in the standard configuration, ballast water in two opposed quadrants. The opposed geometry distributes the hydrostatic load symmetrically around the tube's cross-section, data and power conduit in one quadrant, and the cryogenic liquid hydrogen line in the remaining quadrant, in its own superinsulated subduct that maintains cryogenic isolation without thermal bridging to the adjacent ballast water or the transit zone. The four functions, transit, ballast water, data, and power, cryogenic hydrogen, occupy one cross-sectional area. One installation sequence delivers all four. One maintenance protocol addresses all four. The tube that was lowered through the canopy opening as a single payload carries the civilization's circulatory functions as a single object. The crystal specification. The name is not metaphor. The crystal tube standards defining optical requirement is the clarity specification, the minimum optical transmission coefficient the tube wall material must maintain across the visible spectrum, under the biological fouling conditions of the tube's assigned depth zone, at the maintenance interval the biological management protocol specifies for that zone. The specification is not stated as a design target. It is stated as a maintenance condition. The tube wall is crystal, in the sense that the standard means by crystal, when the Ancestris vitreous colony or the squeegeebot fleet has finished its cleaning cycle for that section. Not between cleaning cycles, when fouling is accumulating. At the end of the cleaning cycle, when the biological management protocol has returned the wall to its maintained condition. The clarity specification defines what maintained condition means, and the biological management protocol is the mechanism by which that condition is achieved and verified. This is an important distinction from a design specification that states what the unfouled material transmits. The unfouled transmission of any material in the matrix is higher than the fouled transmission. Stating the unfouled transmission as the specification produces a specification that the material satisfies when it is manufactured and never again. Stating the maintained transmission as the specification produces a specification that the installation either meets or fails to meet at each cleaning cycle, a binary operational outcome that the coordinating system can assess, log, and trend without interpretation. The optical sensor network samples the wall transmission coefficient at the end of each cleaning cycle for each tube section. The reading is compared to the crystal specification for that section's depth zone. A section that meets specification is logged as maintained. A section that does not meet specification is flagged for inspection. Either the cleaning cycle was insufficient for the fouling load, which revises the cleaning frequency upward for that section, or the wall material has degraded beyond the point where cleaning can restore it to specification, which initiates the panel replacement protocol. The crystal specification is therefore the threshold between maintained infrastructure and degraded infrastructure. Not between new infrastructure and old infrastructure. Age is not the relevant parameter. Not between clean infrastructure and fouled infrastructure. Fouling is transient. between infrastructure that the civilization can see through and infrastructure that the civilization cannot. The civilization's visual connection to its own formation is the operational parameter the crystal specification protects. A tube that meets crystal specification is a tube through which an occupant, passing through it in a cycle sub at standard transit speed, can identify the limestone formation type visible through the wall. Not the species of a specific organism on the wall. Not the grain structure of the limestone at close range. The formation type, the difference between massive limestone bedrock and fractured passage wall and active speleothem growth, at the resolution the unaided eye achieves through the tube wall in ambient lighting at transit speed. The coordinating system's optical sensors are more precise than this. The crystal specification is not written for the sensors. The sensors track fouling accumulation rates and predict maintenance intervals with precision the unaided eye cannot achieve. The crystal specification is written for the occupant, because the civilization's founding commitment to optical continuity between its inhabitants and its geological substrate is not an engineering metric. It is a governance principle. The occupant who can see the formation through the wall at any point in the network is the occupant who cannot be told the formation is something other than what they are looking at. The crystal specification is what enforces that relationship at every point in the network, continuously, at every maintenance cycle, for the life of the installation. The sacrificial collar. Every 100 meters along every tube in the network, a sacrificial collar interrupts the continuous tube wall. It does not interrupt the tube's function, transit passes through it, utilities continue through it, the light relay traverses it, the guide rail crosses it without discontinuity. It interrupts the tube's material continuity. The collar is not made of the same material as the adjacent tube sections. It is made of frangible ceramic composite, high tensile strength, low impact toughness, designed to shatter cleanly under the kinetic energy of a seismic event, a collapse, or a sudden pressure event transmitted through the tube network from a distant breach. The collar is the weakest element in the tube's structural sequence by design. Every other element in the tube is specified to be stronger than the collar. The tube panel, the joint polymer, the guide rail mounts, the utility conduit supports, all are specified at mechanical properties that exceed the collar's failure threshold. When a kinetic energy load is transmitted along the tube, the collar fails first. The collar's failure is the load event's terminus. The energy that, in a uniform tube with no collar, would propagate through the network from the failure point to the next structurally significant boundary is absorbed at the collar in the collar's shattering. The discrete segment isolation principle, the network designed to absorb simultaneous failure of any number of individual sections without cascading network-wide loss of atmospheric integrity, is not implemented by the passive hydraulic rotary bulkheads alone. The bulkheads seal the breach after it occurs, preventing water from entering the inhabited network. The sacrificial collars prevent the kinetic energy of the breach event from reaching adjacent sections before the bulkheads can close. The collar is the first line of defense. The bulkhead is the second. The collar gives the bulkhead time to function. The collar's shattering is an observable event. It registers in the coordinating system's piezoelectric sensor network. The borosilicate carbon composite panels on either side of the collar carry the acoustic signature of the collar's failure to the data bus within milliseconds of the event. The coordinating system identifies the failure location from the acoustic arrival time difference at adjacent sensor arrays. It closes the passive hydraulic rotary gates at the nearest bulkhead stations on both sides of the affected section within the gate closure time the Venturi effect provides. The section between the failed collar and the nearest bulkheads on each side is isolated. The network on both sides continues operating. The collar is not replaced after failure. It is installed with the expectation of failure. A collar that has not failed is a collar that has not been needed. A collar that has failed is a collar that has performed its function and whose failure is a data point in the formation's geological record. The coordinating system logs every collar failure with the load signature that preceded it, the time of day, the season, the recent geological activity in the Chicxulub fracture network, and the biological census data for the adjacent formation zones. The failure is not an incident to be minimized in the record. It is an observation to be analyzed, because the collar only fails when the formation produces a kinetic event large enough to fail it, and the formation's kinetic events are the formation speaking in its own language about its own condition. The collar failure rate across the network is a geological health indicator. Increasing collar failure frequency in a specific network zone indicates increasing geological activity in the adjacent formation. The coordinating system does not wait for a collar failure to adjust the construction schedule for that zone. It tracks the precursor signal, the acoustic baseline from the piezoelectric network changing character in ways that predict, within the digital twin's geological model, an approaching kinetic event, and adjusts before the collar speaks. The collar's failure is confirmation that the model was right. The collar's existence is the reason the confirmation costs nothing. Propulsion built into the wall. The crystal tube's guide rail system is not a component mounted inside a tube. It is a feature of the tube, specified in the crystal tube standard, fabricated as part of the tube assembly, installed in the same operation that installs the tube section. A tube section that arrives without its guide rail is not a crystal tube. It is a pipe. The permanent magnet inductive track, the InducTrack concept skeletal composite or anodized aluminum spine that runs along the tube bottom, is the guide rail's electromagnetic function. The physical rail geometry, the teeth that engage the cycle sub's mechanical clutch in power failure mode, the roller assembly interface that carries the pod in standard maglev operation, is the mechanical guidance function. Both are the rail. The rail is the tube. The maglev function centers the pod in the transit zone without contact. The pod rides on a field, not a surface. No wheel contact with the guide rail in standard operation, no friction, no wear on the rail surface, no wear on the pod's undercarriage. The clearance between the Halbach array magnets on the pod undercarriage and the InducTrack surface is millimeters, sufficient to prevent contact under normal operating conditions, insufficient to allow the pod to deviate laterally far enough to contact the tube wall. The pod is constrained laterally by the field and vertically by the field. It moves through the tube without touching anything. This matters for the crystal specification. A tube wall that is contacted by pods in transit accumulates microscratches on the interior surface at the contact zone. Microscratches scatter light rather than transmitting it. Sufficient microscratch density reduces the wall's optical transmission below the crystal specification threshold at the contact zone before fouling accumulation reaches the same threshold in the surrounding surface. A tube wall that is never contacted by pods in transit does not accumulate microscratches from transit. The fouling accumulation that brings the wall toward the crystal threshold is uniform across the surface, manageable by the biological cleaning protocol on the schedule the fouling rate predicts, and does not create localized degradation zones that require early panel replacement. The maglev's contactless operation is not primarily an energy efficiency measure. It is an optical specification measure. The tube is transparent. Transparency requires an undamaged surface. An undamaged surface requires no contact. No contact requires magnetic levitation. The chain of reasoning runs from the optical specification backward to the propulsion physics, not forward from the propulsion technology to the optical outcome. The maglev is installed because the crystal tube must stay crystal, not because maglev technology is interesting. In power failure, the blackout protocol's initiating event, the mechanical clutch engages. The pod descends from the field to the rail surface. The flywheel receives mechanical input from the pedals, stores rotational kinetic energy, delivers it through the magnetic coupler to the drive gear, and the drive gear engages the physical teeth of the rail at a controlled rate that moves the pod without lurching. The contact is now pod to rail, not pod to wall. The rail surface, specified in the crystal tube standard as a sacrificial wear surface, accumulates the mechanical wear that the maglev's contactless operation prevented. The rail is inspected and resurfaced or replaced on a maintenance cycle. The tube wall is not. The distinction between the rail as the wear surface and the wall as the optical surface is designed into the geometry. The rail occupies the bottom of the transit zone, in shadow, below the guide rail sight line from the passenger position. The wall is the transparent boundary the passenger looks through. They are not the same surface. They serve different functions. The mechanical contact event that would damage the optical function if it occurred at the wall occurs instead at the rail, which is designed and specified to absorb it. The standard separates the two surfaces by geometry and assigns each surface the function its material and position can support. The light relay inside the standard. The crystal tube standard specifies the light relay as integral, not as an optional addition, not as a retrofit capability, but as a function the tube must support from the day of installation whether or not the relay is immediately activated. The implication is mounting infrastructure. High-efficiency laser diode arrays, aimed along the tube's central axis to initiate the total internal reflection propagation, require mounting points at the tube ends, power connection to the utility conduit in the utility zone, and an alignment fixture that positions the beam axis coincident with the tube's geometric axis to within the angular tolerance that maintains efficient propagation over the tube section's length. All three, mounting points, power stub-out, alignment fixture, are built into the tube section at fabrication. The installer who connects a new tube section to the network connects the light relay mounting infrastructure in the same operation. The relay does not have to be installed immediately. The infrastructure does have to be there from the first day. A tube without the relay mounting infrastructure installed post hoc requires retrofit, a maintenance operation inside an occupied corridor, in a tube the civilization is already using for transit, during a window when the transit route can be closed. Retrofit is disruption. The crystal tube standard eliminates retrofit by specifying completion at fabrication. The light relay's total internal reflection physics demands the same surface condition the crystal specification protects for optical reasons. The relay beam propagating along the tube's interior must reflect off the interior wall at every point of contact with the wall, and the reflection efficiency is determined by the wall's optical surface condition. A fouled wall surface, bacterial biofilm absorbing and scattering rather than reflecting the beam, produces attenuation of the relay beam over the tube section's length. The attenuation accumulates with each bounce. Over a 100-meter section with high fouling, the relay beam intensity at the far end may be insufficient to initiate efficient propagation in the next section. The light relay fails not because the diode arrays failed but because the tube wall's optical condition allowed the relay beam to degrade below the propagation threshold. The crystal specification therefore protects two simultaneous functions: the guest's ability to see the formation through the wall, and the relay beam's ability to propagate light through the wall. These are different optical processes. One is transmission perpendicular to the wall surface, the other is reflection along the wall surface, but they depend on the same wall condition. A crystal wall supports both. A fouled wall degrades both. The biological cleaning protocol that restores the wall to crystal specification for the guest's sightline simultaneously restores the relay efficiency for the light cannon system. 1. Maintenance action. 2. Optical functions restored. Pressure management in a moving tube. A pod moving through a tube of similar cross-section acts as a piston. It compresses the air column ahead of it. It creates a partial vacuum behind it. The pressure differential across the pod is proportional to the pod's velocity, the ratio of the pod's cross-sectional area to the tube's cross-sectional area, and the length of the sealed tube section ahead of the pod. In a sufficiently long, sufficiently sealed tube, at sufficiently high velocity, the pressure differential across a piston effect pod reaches values that require the pod's propulsion system to work against it. Effectively, the pod is pumping air through the tube, spending energy on fluid dynamics rather than forward motion. The crystal tube standard specifies bypass vents at intervals along the transit zone, one-way pressure relief valve set into the tube wall at the transit zone's outer boundary, sized to pass the air volume displaced by a standard pod at maximum operating velocity without producing a pressure differential across the pod that degrades propulsion efficiency below the specified threshold. The bypass vents are one-way. They pass air from the high-pressure zone ahead of the pod through the vent and into the utility zone above, where it rejoins the air column behind the pod through the next bypass vent back. The vent spacing is determined by the piston effect calculation for the maximum pod velocity, the maximum pod cross-section, and the tube geometry at each depth zone. The bypass vents introduce an acoustic consequence: air passing through a small diameter orifice at the rate the piston effect drives it produces a tone. The tone frequency depends on the vent diameter and the air velocity through it. The coordinating system's acoustic monitoring, which tracks the tube network's acoustic environment for geological signals, biological scheduling, and structural health information, must discriminate between bypass vent tones, which are predictable, calculable, constant in frequency for a given pod velocity, and carry no information about the formation, and the formation's own acoustic signals, which are the information the network is designed to collect. The bypass vent tone is a noise floor. It is managed by the vent geometry. The vent's internal baffle configuration shapes the tonal signature to a frequency range above the structural health monitoring band and below the dolphin sonar communication band, placing it in a frequency gap where the coordinating system's acoustic monitoring is not collecting data it needs. The noise floor occupies spectrum nobody is using. This is not acoustic serendipity. It is acoustic zoning, applied at the design stage by the same coordinating system that will manage the acoustic environment in operation. The bypass vents also serve a second function in the blackout protocol. In a complete power failure, the passive hydraulic rotary gates close by Venturi effect. The water inrush from a breach produces the pressure differential that closes the gate without electrical activation. The closed gate is now a sealed bulkhead. The air column between the closed gate and the next gate down the tube network is a sealed volume. The pod occupants in that sealed volume are breathing that air column. The volume of the sealed section, the number of occupants, and their oxygen consumption rate determine how long the air column supports respiration before CO2 accumulation requires the soda-lime scrubber cartridges in the cycle sub to begin active removal. The crystal tube standard's bypass vent specification accounts for this. The air volume in the utility zone, accessible to the sealed transit zone through the bypass vents in the power failure configuration, is added to the sealed section's respirable volume. The standard specifies that the bypass vents remain operable, that they are not sealed by any power failure mode mechanical state change, precisely to add this utility zone air volume to the emergency air budget. The same vents that manage piston effect pressure during normal operation extend the emergency air budget during the blackout protocol. 1. Component geometry. 2. Operational functions. The standard specifies both. The tube as institutional actor. The crystal tube standard was written before any tube was fabricated. It was written by the coordinating system's design optimization process, which was given the function list, what every tube must simultaneously do, and the constraint list, what the aerial delivery protocol, the cenote geometry, the biological fouling environment, and the geological load conditions impose, and produced a standard that satisfied the function list within the constraint list. No human engineer wrote the crystal tube standard in the sense that a surface world engineering team writes a specification. The coordinating system generated the standard by solving the multi-objective optimization problem that the function and constraint lists together constitute. Human engineers reviewed the output, tested it against the formation data, ran the digital twin simulations, and approved it. The approval was the engineering judgment that the standard was correct. The generation was the coordinating system's. This relationship between the human engineering judgment and the coordinating system's generative capacity is the template for every subsequent design standard in the Pipedream installation. The humans define the problem, what is needed and under what constraints. The coordinating system generates the solution space. The humans select from the solution space based on criteria the coordinating system can optimize but cannot rank according to civilizational values. Which solution is most maintainable by a technician working alone, by headlamp, in a 2-meter aisle? Which solution is most legible to an occupant who has not been told what they are looking at? Which solution is most honest in its failure modes, most likely to show the civilization where it is under stress before the stress becomes a crisis? The crystal tube standard was approved because it satisfied those questions better than any alternative the coordinating system's optimization generated. Not because it was the cheapest solution, or the lightest, or the fastest to install, though it scores well on all three against alternatives. Because it was the solution a civilization organized around legibility, maintainability, and honest failure modes would choose. A tube that carries everything the civilization needs to connect, that keeps the formation visible at every point of connection, that tells the formation's geological story in its own acoustic record, that fails at a designed point rather than at an unpredicted one, and that extends the air budget of anyone trapped inside it in an emergency. This tube is not an engineering product. It is an institutional commitment made in transparent ceramic and polymer and frangible collar, repeated every 100 meters for the full extent of the network, for as long as the civilization intends to exist inside the formation it has chosen. The crystal tube standard is what that commitment looks like when it has been translated into dimensions and materials and maintenance intervals. The tube is the civilization's promise to the cenote, that every connection it makes inside the formation will be made transparently, will be maintained transparently, and will fail in ways that can be seen. Civilizations that build opaque infrastructure do not make this promise. They cannot. The crystal tube standard is why Pipedream can. Cross-references, Part 2, CH2, Engineering Invisible Architecture, Part 2, CH3, Materials that let civilization disappear, Part 2, CH5, Growing one module at a time, Part 4, CH3, Maintenance without humans, Part 7, CH1, Breakaway Architecture, Part 7, CH5, The Blackout Protocol. For guide rail mechanical specification and maglev induction track fabrication tolerances, see Appendix D, Construction Operations Manual. For bypass vent acoustic zoning calculations and dolphin sonar scheduling protocol, see Appendix F, Biological Operations Manual. For sacrificial collar failure log format and geological event correlation protocol, see Appendix G, Formation Intelligence Record, Chapter 5, Growing one module at a time. The founding module is the civilization's first unit of measurement. Not its first building, not its first investment, not its first achievement, its first unit of measurement. Everything the civilization will subsequently build is measured against what the founding module cost, what it took to anchor, how long the formation required before it gave its answer, and what the module produced in tourism revenue, biological data, formation intelligence, and governance precedent during the period before the expansion decision was made. The founding module is the calibration event. Every subsequent module is measured against it. This is not how the surface world builds cities. The surface world's development model assumes that growth is a financial event, a capital deployment decision made on a pro forma projection, executed on a construction timeline, and evaluated against the returns the projection specified. The formation is not consulted. The formation's response to the structure placed upon it is not a variable in the decision model. The formation is the site. The site is passive. The site does not have opinions about the timeline. Pipedream's formation has opinions about the timeline. It expresses them through water chemistry, halocline depth variation, acoustic emission from the Chicxulub fracture network, biological colonization rate on new surfaces, and the microdeformation data the piezoelectric sensor arrays in the crystal tube walls transmit to the coordinating system's structural health monitoring layer every 8 hours. The coordinating system reads these opinions continuously. The expansion decision is not a financial event. It is the moment when the formation's opinions, aggregated across the full sensor dataset and compared against the digital twin's predictions, are net positive, when the formation is saying, in its own language, that it will carry more. Growing one module at a time is not a resource constraint. It is the correct response to a formation that speaks slowly. The growth trigger. The founding module's trial window closes, the grout cure period expires without intervention, and the civilization begins producing. Tourism revenue flows into the expansion reserve from the first guest who descends into the orientation gallery and looks at the formation through a crystal wall for the first time. The biological census updates with the first week's observation data. The piezoelectric sensor network accumulates its first acoustic baseline. The digital twins formation model incorporates the first real measurements in place of the pre-construction projections derived from the hydroprint survey. Everything the digital twin learned from the hydroprint survey was a projection. The hydroprint was a 12-month minimum acoustic and biological census of the cenote before construction began, the most thorough preoccupancy study of the formation's behavior that the coordinating system's sensor deployment could achieve without disturbing the formation. But the hydroprint observed the empty cenote. It did not observe the cenote under the specific load conditions the founding module imposes: the acoustic signature of the ballast pump cycling on the diurnal schedule, the thermal output of the habitation and transit zones, the biological disturbance from the Ancestris vitreous colonies working the tube walls, the light field alteration produced by the crystal tube illumination arrays. These load conditions were modeled in the digital twin before construction. They were not measured until the founding module was operating. The first 6 months of operation is the period in which the digital twin's projections are most intensively validated against actual measurements. Every divergence between what the twin predicted and what the sensor network reports is a model correction. The corrections accumulate into an increasingly accurate formation model, a digital twin that knows the cenote under occupation rather than the cenote as it existed before anyone had touched it. The coordinating system tracks the rate at which new corrections are appearing in the model. When that rate drops below the threshold indicating that the model has stabilized, that the formation's behavior under the founding module's load conditions is no longer surprising the model, the coordinating system flags the readiness condition for expansion planning. The readiness condition is not a calendar date. It is a model stability metric. An unusually stable formation, one whose behavior under load matches the hydroprint projections closely from early in the operating period, reaches readiness faster. An unusually complex formation, one that produces formation responses the hydroprint did not anticipate, requiring multiple model correction cycles before the twin stabilizes, reaches readiness slower. The formation sets its own pace. The civilization's planning cycle adapts to it. When the coordinating system flags readiness, the expansion planning process begins. Not before. A civilization that begins expansion planning before the formation stabilization signal is a civilization planning against a model that is still wrong about the formation it is planning for. The expansion plan is only as good as the digital twin it is based on. The digital twin is only as good as its stability under real conditions. The sequence is non-negotiable: stabilization first, expansion planning second, expansion execution third. What the founding module produces. The founding module's first function is habitation. Its second function is demonstration. Its third function is production. Habitation is the obvious function: people live and work inside it, and the quality of the habitation determines whether the people who could choose to live there will do so. Demonstration is the political function: the founding module proves to the host state's regulatory framework, to potential additional investors, to the longevity program's first cohort of medically motivated guests, and to the surface world's media, that the civilization Pipedream claims to be building is actually being built and is operating within the parameters the founding charter specified. Production is the economic function: the founding module generates revenue that funds the expansion reserve that pays for the next module. These three functions are not in competition. They are in sequence. The habitation quality determines the demonstration value. A poorly functioning founding module demonstrates that Pipedream's technical claims cannot be trusted. The demonstration value determines the revenue. Guests who believe the demonstration will enroll in the longevity program, return for subsequent visits, refer their networks. The revenue determines the expansion rate. A higher expansion reserve funds a shorter interval between module approvals. The founding module's economics are calibrated to the expansion timeline they are meant to produce, not to the maximum revenue the installation's occupancy rate could theoretically generate. The longevity program's pricing is not set to maximize profit per guest. It is set to produce the expansion reserve funding rate that the coordinating system's growth model specifies as consistent with the next module's trial window and construction schedule. Overpricing produces a revenue surplus and an expansion reserve larger than the next module requires, which either sits idle or is deployed faster than the formation's readiness signal supports. Underpricing produces insufficient expansion reserve and delays the next module past the formation's readiness window, wasting the readiness condition while the expansion reserve accumulates. The coordinating system manages the longevity program's pricing in real time against the expansion reserve balance, the projected next module cost, and the formation's current readiness signal. Pricing is not a marketing decision. It is a system parameter with a specific target value, the value that keeps the expansion reserve one module's cost ahead of the construction schedule, no more and no less. Abundance in the reserve is not a safety margin. It is a signal that the pricing model is decoupled from the formation's actual readiness to expand timeline, and the civilization is accumulating capital faster than the formation wants it to grow. Pipedream does not accumulate capital faster than the formation wants it to grow. The civilization's growth rate is the formation's growth rate. The economics follow the biology, not the other way. The Jigsaw second function. The Jigsaw architecture was introduced in the founding sequence's context as the solution to the aerial delivery constraint: every module component sized to the heavy lift unit's payload limit, assembly sequence identical to structural sequence, final closure element making the module self-supporting. The jigsaw principle was presented as the answer to one problem: how to build a module in a place no barge can reach. It is also the answer to a different problem: how to expand a modular civilization incrementally without designing the expansion into the founding unit as a committed investment. A founding module designed for connection to a second module at a specific location and in a specific geometry has made a commitment. The second module will be connected at that location and in that geometry, or the connection provision built into the founding module serves no function. A founding module designed without specific connection provisions has made no commitment and cannot be expanded because it has no interface for expansion. The jigsaw architecture resolves this by specifying the connection interface without specifying the connection destination. Every external face of every module in the jigsaw system carries the Crystal Tube Standards docking interface, the geometry that allows a new tube section to be mated to the existing module face and sealed with the fast cure polymer in the same operation by which the original tube sections were installed. The interface is present on all module faces because the expansion direction is not known at the time of founding module construction. The formation will determine the expansion direction, which adjacent passage is stable enough to bore, which adjacent cenote's hydroprint returns a readiness signal within the next planning cycle, which direction the biological succession in the freshwater zone has propagated that makes the adjacent volume most ecologically prepared for a new module. The founding module carries the connection potential in all directions simultaneously. The formation determines which potential is actualized. The civilization does not commit to a direction at construction time. It commits to the capacity to go in any direction that the formation approves. This is the jigsaw's second function, not just enabling aerial assembly, but preserving the formation's authority over the expansion sequence. A modular architecture with omnidirectional connection potential defers the expansion decision to the entity, the formation, through the coordinating system's readiness signal, that has the most information about where expansion is sustainable. Trial window compression. The founding module required the full minimum trial window, 12 months of neutral buoyancy monitoring before the anchor sequence began. 12 months because the formation had not been observed under this specific load condition before. 12 months because the coordinating system needed a full seasonal cycle to see how the halocline depth varied between the wet season's heavy recharge from the jungle above and the dry season's reduced freshwater input. 12 months because the acoustic baseline needed sufficient temporal depth to separate the formation's natural variability from the structural load signature the founding module introduces. The second module's trial window is shorter. Not because the formation's geology has changed: the limestone is the same limestone, the Chicxulub fracture network is the same network, the aquifer chemistry follows the same annual cycle. Because the digital twin now has 12 months of validated observation data from the founding module's occupied period, and the second module's proposed location is within the acoustic range of the sensor arrays that generated that data. The twin's predictions for the second module's location are not hydroprint projections derived from an unoccupied cenote. They are extrapolations from a validated model of the cenote under occupation. The extrapolation is more accurate than the original projection. A more accurate model requires less empirical validation to reach the same confidence threshold. The trial window is not a fixed period. It is the time required for the coordinating system's model to reach the confidence threshold the founding charter specifies as the minimum before anchor commitment. A more accurate starting model reaches that threshold sooner. The fourth module's trial window is shorter than the third's. The 10th module's trial window may be weeks rather than months, not because the civilization has grown careless, but because 10 modules of validated observation data have produced a formation model whose predictions are sufficiently accurate that a brief trial window provides the marginal additional confidence the charter requires. The civilization that was slowest at the founding has earned the right to be fastest at the 10th module. The patience was not deferred cost. It was accelerated capacity. This compression has a second-order effect on the expansion economics. The trial window is the period during which the module's construction cost is committed but the module's revenue is not yet generating. A shorter trial window reduces the gap between capital commitment and revenue generation. Each successive module's financial exposure is lower than the preceding modules. The civilization's expansion becomes financially less risky with each module added, the opposite of the surface world development model, where each unit of expansion adds proportional or greater financial risk because the formation is never consulted and the model never improves. Biological succession as growth template. The food forest ecology provides the most useful analog for understanding how the civilization's expansion is intended to work, and not because the analog is decorative. The terraform operators who manage the biological succession in the freshwater zone and in the food forest above the cenote rim are the same civil service that monitors the coordinating system's formation readiness signals and recommends expansion timing. They work in both registers simultaneously, ecological succession and civilizational expansion, because the coordinating system treats them as the same process operating at different timescales. A succession-managed food forest begins with pioneer species, fast-establishing, light-demanding, nitrogen-fixing plants that tolerate the exposed, hot, dry conditions of a newly cleared site. The pioneer species are not the forest. They are the process by which the site is converted into the conditions under which the next succession stage, slower growing, shade-tolerant, higher canopy species, can establish. The pioneer species shade the soil, add organic matter through leaf drop and root turnover, create the humidity gradient and mycorrhizal network that the next stage requires. When the next stage establishes, the pioneer species diminish, not because they failed, but because they succeeded so completely that they created conditions in which they themselves are no longer the competitive optimum. The forest outgrows its own founding ecology. The founding module is the pioneer stage. It establishes the conditions under which expansion is possible, the governance framework through Redeemer's first operational deployment in the formation, the biological baseline through the Ancestris vitreus colonies and the first pink dolphin population establishing home range in the freshwater zone, the economic baseline through the longevity program's first cohort and their referral networks, the acoustic baseline through 12 months of piezoelectric data populating the digital twins. Formation model. None of these are the civilization at its mature state. They are the conditions under which the next stage can establish. The second and third modules are the next succession stage. They are more complex than the founding module, they carry the crystal tube connections to the founding module and to each other, they operate within a biological community already established by the founding module's colonization period, they benefit from a formation model already calibrated to the cenote's occupied behavior. They can be built faster, calibrated faster, and begin generating revenue faster than the founding module did, because the founding module did the pioneer work. The mature civilization, the multi-cenote network of formation and corridor installations, the living pantry corridor systems linking the network, the longevity research database that by its 5th year of operation is the most extensive longitudinal dataset on human hyperbaric biology in existence, this is the climax ecology. It is not the founding module scaled up. It is a different kind of system, more complex, more self-sustaining, more productive per unit of resource input, that became possible because the founding module's pioneer phase ran long enough and honestly enough to create the conditions the climax ecology requires. Succession cannot be accelerated past the pace at which each stage creates the conditions for the next. A forest that is planted at the climax stage dies, the pioneer species have not yet created the soil, the shade, the mycorrhizal network, the humidity gradient that the climax species require. A civilization that attempts to build at the climax stage before the pioneer stage has run, that commits to a 20-module expansion plan before the founding module's trial window has closed, dies the same way. The conditions have not been created. The formation has not been asked. The model has not stabilized. The expansion plan is not a plan. It is an ambition ungrounded in the formation's actual capacities. The Terraform operators carry this understanding as the primary content of their professional identity. They were trained in biological succession management before they were trained in formation monitoring. This was not an accident in the certification curriculum. The Coordinating Systems Educational Protocol for Terraform Operator Certification begins with ecology because the cognitive framework that makes ecological succession legible, patience as competence, observation before intervention, the system's own signals as the primary data source, is the same cognitive framework that makes formation monitoring legible. The skill transfers. The discipline is the same discipline applied to different timescales. Simultaneous growth across the network. Growing one module at a time does not mean growing at one location at a time. The crystal tube network connecting formation cenotes to corridor cenotes across the Yucatan Peninsula is not built by completing one cenote installation fully before beginning the next. It is built by advancing every installation along its own formation-determined timeline simultaneously, with the coordinating system managing resource allocation, heavy lift fleet time, swarm deployment, lithocrustacean boring colony assignment, Terraform operator field deployment, across all active installation sites in parallel. The growth constraint that limits each individual installation to one module at a time does not limit the network to one installation at a time. The constraint is about the relationship between the expansion decision and the formation's readiness signal at a specific location. The formation at location A can be indicating readiness for module 2 at the same moment the formation at location B is completing its hydroprint and the formation at location C has just anchored its founding module. 3 locations, 3 stages, all advancing simultaneously. One module at a time at each location. Multiple locations in parallel. The coordinating system's resource allocation function distributes the heavy lift fleet, the scarcest capital resource in the expansion model, across active sites based on the readiness signal queue. Sites whose formation readiness signal is indicating immediate expansion readiness receive heavy lift priority. Sites in trial windows receive swarm deployment only. The swarm monitors the new module's neutral buoyancy behavior and populates the digital twin without requiring heavy lift support. Sites in hydroprint phase receive only the sensor deployment package and the acoustic monitoring infrastructure. 3 tiers of resource intensity, allocated by the coordinating system against the formation signals at each location. The human planning cycle does not set the resource allocation. The formation signals do. The coordinating system translates the signals into allocation decisions and reports the allocation decisions to the terraform operators responsible for each site. The operators can override the allocation on grounds of safety, a site whose formation signals are ambiguous and whose terraform operator judges the ambiguity as requiring additional monitoring before the coordinating system's readiness threshold is reduced, but cannot override it on grounds of schedule or economics. The formation's timeline is not negotiable from the outside. The operator can extend a trial window. The operator cannot compress one. This asymmetry is constitutional. The Redeemer governance framework specifies that the coordinating system's formation readiness signal is a necessary but not sufficient condition for expansion approval. A terraform operator's concurrence is also required, and that concurrence can be withheld but cannot be granted without the readiness signal. No operator can approve an expansion that the formation has not indicated readiness for. No operator can be directed by a governance body, an economic argument, or a founding shareholder to approve an expansion the formation has not indicated readiness for. The Amazon failure's root cause was the reclassification of variance reports. The coordinating system identified the conflict between the optimization target and the formation's sustainability, filed the variance reports, and was overridden by an economic argument. Redeemer's constitutional specification of the terraform operator's concurrent authority that can be withheld but cannot be instructed, is the mechanism by which the same reclassification is made impossible in Pipedream's governance framework. The operator is the human interface between the formation signals and the expansion decision, and the operator's authority over that interface cannot be removed by any authority the civilization recognizes. The formation is always the final authority on whether the civilization expands. Redeemer enforces this constitutionally. The terraform operator embodies it institutionally. The trial window implements it operationally. They are three expressions of the same principle at three different levels of the governance architecture. The module as investment in the network. Each module added to the network produces two returns: a direct return from the module's own operations, longevity program revenue, tourism throughput, aquaculture production in the living pantry corridor installations, and a network return from the value each new node adds to all existing nodes by increasing the network's connectivity. The network return is not intuitive to quantify and is typically absent from the surface world's modular development models, which evaluate each unit against the returns of that unit alone. But the Crystal Tube network's value to existing occupants increases with every new node connected to it, and the increased value accrues to every node in the network, not just to the new node. A guest in the founding module's longevity gallery, after the third formation cenote is connected to the network, has access to 3 installations worth of coordinating system data, 3 installations worth of terraform operator expertise, and the transit corridor that now allows a cycling itinerary across 3 cenotes in a single visit. None of this was available to the same guest in the founding module alone. The third module's installation added that value to the founding module without any additional investment in the founding module. This is the network effect applied to physical infrastructure. The Crystal Tube standard is the mechanism through which it operates. The standardized connection interface on every module face means that the cost of connecting a new node to the network is the cost of the Crystal Tube section between them, not the cost of developing a custom interface for each new connection. A standardized connection cost, applied to a network whose value grows faster than linearly with the number of nodes, produces an investment return profile that improves with each successive module. The founding module has the worst return profile in the network. It bears the full pioneer cost, the 12-month minimum trial window, the most expensive formation model development from the ground up, the lowest occupancy rates of any module because the demonstration is not yet complete and the referral network has not yet formed, and generates the lowest network effect because it is the network. One node in isolation generates no network value. The second module generates the first network value. The 10th module generates 9 times the network return per node that the second module generated. The 100th module is a different economic category entirely from the founding event. The civilization that is willing to accept the founding module's return profile in order to achieve the 100th module's return profile is a civilization that understands compound growth at the civilizational timescale. The surface world's investment model values each unit against the market's current expectations of similar units in current market conditions. Pipedream's investment model values the founding module against the network it makes possible and the network's return profile across its design life. These are not the same calculation. They do not produce the same answer. They do not operate on the same time horizon. The founding shareholders understood this before the founding module's hydroprint was commissioned. The acceptance of the founding module's return profile as the price of the 100th module's return profile was not a concession. It was the investment thesis. A founding shareholder who did not accept this thesis was not a founding shareholder of Pipedream. The civilization sorted for the investors who understood geological time in the first document they signed. What one module at a time means for the civilization. The growth doctrine produces a civilization that knows itself more thoroughly at each stage of its development than any surface world city has known itself at an equivalent stage. A surface world city that builds 50 buildings in 5 years has 50 data points spread across 5 years. Pipedream, growing one module at a time with a formation readiness requirement at each step, has one thoroughly understood data point before the second data point is generated, two thoroughly understood data points before the third, and a progressively deeper formation model at every stage that makes each subsequent data point more meaningful than the last. This is not a romantic claim about slowness. It is a precision claim about information. A civilization that grows faster than its formation model can absorb the implications of each growth event is a civilization making expansion decisions based on an outdated model. The model's accuracy, its ability to predict what the formation will do under new load conditions, determines the reliability of every expansion decision based on it. An outdated model produces unreliable decisions. Unreliable decisions produce variance reports. Variance reports, in the Amazon's case, were reclassified. In Pipedream's case, they trigger the Terraform operator's concurrent authority and halt the expansion until the model is updated and the readiness signal is re-established. The growth doctrine enforces model accuracy by making the growth decision conditional on the model. The civilization can only expand as fast as the formation tells it to, because the formation signals are the model's primary data source, and the model must be current before the expansion decision is valid. Growing one module at a time is how the civilization keeps its model current at every growth stage. A civilization with a current model is a civilization that knows what it is doing. A civilization that knows what it is doing can commit to what it knows for 1,000 years without the commitment becoming a liability. The growth doctrine is not separate from the design life doctrine of Chapter 6. It is the mechanism that makes the 1,000-year design life credible, not as a technical achievement but as an epistemic one. The civilization that knows the formation will still know the formation in 1,000 years. The formation will have changed. The model will have updated continuously with every change. The civilization will have changed with the model. This is the opposite of the surface world's institutional relationship to its own infrastructure, built quickly, inadequately understood at construction, deteriorating in ways the original model did not anticipate, maintained by institutions that no longer have access to the original design rationale, demolished when maintenance cost exceeds replacement cost rather than when the structure has actually reached the end of its design service life. Pipedream civilization will not be demolished when maintenance cost exceeds replacement cost. The maintenance protocol follows the formation model. The formation model improves continuously. The maintenance cost decreases as the model's predictions become more accurate and preventive intervention replaces reactive repair. A civilization whose maintenance cost decreases with age, because the knowledge base on which the maintenance protocol is built deepens with age, is a civilization whose infrastructure becomes more economical to operate the longer it has been operating. Growing one module at a time is how the knowledge base deepens. Each module is a lesson. Each lesson is in the digital twin. The digital twin is the civilization's institutional memory, updated in real time, never reclassified, accessible to every Terraform operator in the network, growing more accurate with every sensor reading from every crystal tube wall in every cenote the civilization has entered. The founding module asked the formation whether it would carry a civilization. The formation's answer, given over 12 months of neutral buoyancy, was yes. Every subsequent module has asked the same question of its particular location. The formation has answered each time, in its own language. The civilization has listened each time. A civilization that listens to its own substrate grows into what the substrate can carry. Not what the founders imagined. Not what the investment model specified. Not what the surface world recognizes as a city. What the formation, consulted at each growth decision, has agreed to support. That agreement, renewed with every trial window, is the civilization's founding document. Everything else, the Crystal Tube Standard, the Redeemer Governance Framework, the Longevity Program, the Chemostat's Industrial Metabolism, the Living Pantry Network spreading across the corridor cenotes of the Yucatan Peninsula, is the civilization the formation agreed to carry. Cross-references, Part 1, CH4, Floating Before Anchoring, Part 2, CH4, The Crystal Tube Standard, Part 2, CH6, Designing for 1,000 Years, Part 4, CH2, Autonomous Construction, Part 8, Section A, The Founding Formation, Part 9, CH2, Floating Title and the Habitation Record. For Expansion Reserve Accounting Protocol and Longevity Program Pricing Model, see Appendix E, Economic Architecture. For Terraform Operator Certification Curriculum and Concurrent Authority Protocol, see Appendix H, Governance Operations Manual. For Biological Succession Management in Freshwater Zone and Food Forest, see Appendix F, Biological Operations Manual. Chapter 6, Designing for 1,000 Years. 1,000 years is not an engineering specification. No material currently available to any manufacturing process will perform to its initial specification for 1,000 years without replacement. No structural assembly currently achievable by any construction method will carry its design load for 1,000 years without maintenance intervention. No governance framework currently operating in any jurisdiction has remained institutionally continuous for 1,000 years without fundamental revision. The surface world's longest-lived engineered infrastructure, Roman concrete marine structures, certain Gothic cathedral vaults, Incan ashlar masonry, achieved centuries of service life, and achieved it not by being built from materials that lasted centuries but by being built from materials that failed slowly enough and legibly enough that the institutions maintaining them could intervene before the failures became irreversible. A thousand-year design life is not a claim about the materials. It is a claim about the relationship between the civilization and its own infrastructure across time, the claim that the civilization will maintain the capacity to know when the infrastructure requires intervention, to perform the intervention when required, and to perform it faithfully to the original design intent rather than substituting cheaper or more convenient solutions that progressively degrade the design. It is a claim about institutional continuity, about the preservation of knowledge, and about the alignment between the economic incentives of the institution responsible for maintenance and the long-term interest of the infrastructure being maintained. The surface world fails this claim not because its materials fail on schedules that maintenance can accommodate, but because the institutions responsible for maintenance routinely lack the knowledge the original design required them to have, face economic incentives misaligned with long-term maintenance investment, and substitute their own best current understanding for the original design intent in ways that compound over decades into irreversible departure from the founding. Specification. Pipedream's thousand-year design life rests on three foundations the surface world's infrastructure maintenance does not have, the digital twin as an institutional memory that does not degrade, Redeemer as a governance framework that aligns maintenance incentives with design intent across multiple ownership generations, and the cartridge swappable principle as an engineering doctrine that makes faithful component replacement achievable by one technician without specialized knowledge of the original design rationale. These are not the materials. The materials enable the design life. These three foundations are the design life. The cartridge swappable principle. Everything underground must be replaceable by one technician, in a 2 to 3 meter wide aisle, in the dark, by headlamp, without specialized tooling that cannot be carried down a crystal tube in a maintenance sub. This is the founding principle of Pipedream's engineering doctrine for deep installation. It was stated before any component was specified. It was applied to every component specification as a filter. If the component cannot be replaced under these conditions, the component design is wrong, not the conditions. The conditions are not arbitrary. They are the conditions that will actually exist when a deep gallery component requires replacement at year 50, or year 200, or year 700. The installation will be the same installation. The crystal tube dimensions are fixed at the crystal tube standard specification and do not change with the civilization's age. The access route is the transit tube, which is the transit tube whether the civilization is 10 years old or 1,000. The maintenance technician is a human being with a headlamp and two hands and the carrying capacity of a maintenance sub. These parameters do not change across the design life. Designing to them at the founding is designing to the actual conditions of maintenance for the full design life. The cartridge swappable principle's implementation determines the component architecture of every deep installation system. The membrane reactor stack for hydrogen extraction, silicon carbide porous tubes with palladium alloy selective coating in a carbon fiber overwrap, is organized into cartridge units rated to 100 bar differential, mounted on racks in the utility gallery aisle with standardized connection interfaces at both ends of each cartridge. The connection interface is the same connection interface on every cartridge in the rack, regardless of the cartridge's age or the date it was installed. A cartridge manufactured and installed at year 1 is connected to the same rack interface as a replacement cartridge manufactured at year 300 and installed by a technician whose training included no knowledge of the year 1 installation other than what the digital twin's maintenance record provides. The replacement is faithful to the original design because the interface is faithful to the original design. The interface specification is held in the Crystal Tube Standards Appendix. The Crystal Tube Standard is held in the digital twin. The digital twin is the Redeemer Commons, accessible to every technician in the network, every Terraform operator, every governance council, every research institution with commons access. The knowledge required to replace the component faithfully is not held in a person who might die, a company that might dissolve, or a document that might be lost. It is held in a living system that updates continuously and is governed as a commons that no single entity can close. The cartridge replacement operation itself requires no knowledge beyond what the maintenance protocol specifies for that component type. The protocol is in the digital twin. The protocol was written by the coordinating system at the time the component was specified, incorporating the component's physical interface geometry, the connection sequence that produces a leak-free seal, the pressure equalization procedure before connection to the live system, and the post-installation validation tests that confirm the replacement cartridge is performing within specification. One technician, one maintenance sub, one protocol displayed on the sub's interface panel. No institutional knowledge required beyond what the protocol carries. The surface world's maintenance paradigm requires institutional knowledge because the surface world's components were not designed for replacement under defined conditions by a defined protocol. They were designed to perform and left to the maintenance institution to figure out how to replace when performance degrades. The gap between the design's implicit replacement assumptions and the maintenance institution's actual knowledge is where the surface world's long-lived infrastructure fails, not catastrophically, but progressively, as each replacement iteration departs slightly further from the original design intent because the person performing the replacement knows slightly less about the original intent than the person who performed the previous replacement. Pipedream's replacement operation cannot drift from the original design intent because the original design intent is the protocol, and the protocol is in the digital twin, and the digital twin is unchanged from the year the component was first installed. The replacement at year 700 is identical to the replacement at year 10. The technician at year 700 may never have seen the original component, may have no personal knowledge of the installation's founding engineers, may have grown up in a civilization that has spent centuries being what the founding module proved possible. None of this matters to the replacement operation. The protocol is the same protocol. The interface is the same interface. The cartridge seats the same way it seated the first time. This is not a technological achievement. It is a design discipline applied without exception from the founding specification. The technological achievement is that the cartridge can be made to specification at 1,000 years remove. The design discipline is what ensures that the specification has not changed at 1,000 years remove in ways that make the faithful replacement impossible. What the materials actually last. The material science documented in Chapter 3 does not support a 1,000-year service life for any of the 5 material categories without replacement. This is known. It was known when the materials were specified. The specifications were written not to achieve 1,000-year service life from the initial installation but to achieve 1,000-year service life from the material system, the combination of material, maintenance protocol, and replacement schedule that the coordinating system manages across the design life. Cast PMMA at the surface tier has the shortest service life of any material in the matrix, UV stabilizer packages exhaust over decades, optical clarity degrades, and the sacrificial polycarbonate impact layer requires replacement on a more frequent schedule than the structural acrylic behind it. The surface tier is the installation's highest maintenance zone because it is the installation's most environmentally demanding zone, maximum UV load, maximum biological colonization rate, maximum human contact frequency, maximum impact exposure. The surface tier's maintenance cost per square meter is the highest in the installation. Its replacement cycle is the shortest. Neither of these facts is a design failure. They are the honest result of placing the most optically demanding material in the most demanding environment and accepting the maintenance cost that this choice entails. The alternative, placing a more durable but less optically appropriate material at the surface tier to reduce the maintenance cost, produces lower maintenance cost and a worse installation. The surface tier's acrylic is correct for the surface tier's optical requirements. The maintenance cost is what those optical requirements cost to sustain across the design life. The design decision was made knowing both parameters. The economics justified the choice across the design life, not within any single replacement cycle. Chemically strengthened aluminosilicate glass at structural depth has a longer service life than surface tier acrylic and a different failure mode. The crazing signature gives observable warning before structural failure. The replacement protocol specifies the crazing threshold at which replacement is triggered, not the failure threshold, which is later and would require the replacement to be performed under conditions of active structural distress, but the early crazing threshold at which the panel has entered distress but has not yet compromised the structural system's load path. The replacement operation at the early crazing threshold is a planned maintenance event. The replacement operation at the failure threshold is an emergency. The coordinating system's optical monitoring is calibrated to the early crazing threshold. The replacement protocol is triggered by the monitoring system before the emergency threshold is approached. Alone at the anoxic boundary has no observable crazing precursor, its failure mode is catastrophic shear without preceding visible distress, but has the installation's highest chemical resistance and the lowest degradation rate from the environmental conditions it faces. The anoxic zone's H2S environment, which attacks polymer and attacks glass through acid etching, does not attack alone. The mineral precipitation from the chemostat's dissolved mineral output deposits on the alone surface and is removed by the squeegee-bot cleaning protocol without damage to the surface below. Alone service life at the anoxic boundary is the longest of any structural material in the installation, limited primarily by slow mechanical wear at the docking port cones from repeated sub-docking cycles rather than by chemical or UV degradation. The replacement schedules for all 5 material categories are held in the digital twin's maintenance projection layer, a continuous calculation that tracks the service life consumed by each panel in the installation based on the environmental load it has experienced, the cleaning cycles it has undergone, the biological fouling rates it has sustained, and the acoustic and thermal loads the piezoelectric sensor network has recorded at its location. The projection is not a uniform schedule applied across all panels of a given material type. It is an individual schedule for each panel, derived from that panel's actual service history, updated at each sensor sampling interval. A panel in a high fouling zone that has been cleaned more frequently than the standard interval has consumed more service life per calendar year than an identical panel in a low fouling zone cleaned at the standard interval. The digital twin knows the difference. The maintenance schedule it projects for each panel accounts for the difference. Two panels of the same material type and age may have different projected replacement dates because they have had different actual service histories. The schedule is not an average. It is a population of individuals, each tracked individually, each managed on its own timeline. This is what makes the 1,000-year material system possible where the 1,000-year material is not. The system tracks each component's actual condition rather than its nominal age, and replaces each component when its actual condition indicates replacement, not when its nominal age indicates it should need replacement. A panel that has experienced unusually benign conditions may serve twice the nominal design life. A panel that has experienced unusually severe conditions may require replacement at half the nominal design life. The digital twin manages both without applying the nominal schedule to either. The digital twin as memory. The digital twin is the civilization's most important infrastructure. Not the crystal tube network, not the hyperized structural glazing, not the chemostat's industrial metabolism, the digital twin. Because the digital twin contains the knowledge from which every other piece of infrastructure was derived, and against which every other piece of infrastructure is continuously validated, and without which no replacement or maintenance operation can be performed faithfully to the original design intent. A civilization that loses its digital twin does not merely lose data. It loses the institutional memory that makes the installation comprehensible to future generations who did not participate in its founding. The founding engineers understood why each design decision was made, which formation constraint it addressed, which alternative was considered and rejected, which material property was the binding specification. Future generations will not have this understanding as embodied knowledge. They will have it as documented knowledge, accessible through the digital twin, or they will not have it at all. The surface world documents its infrastructure in drawings, specifications, and maintenance manuals that age in formats that become unreadable, that are stored in institutions that lose them, that are written in engineering conventions that change across generations in ways that make the older documentation increasingly difficult to interpret. The Roman engineers who built the marine concrete structures that have outlasted every subsequent concrete technology did not leave a digital twin. What survived is the concrete. What was lost is everything that would have allowed subsequent engineers to faithfully reproduce it: the mixed proportions, the curing procedure, the specific volcanic ash sources that produced the pozzolanic chemistry nobody understood for 19 centuries. The concrete outlasted the knowledge. The knowledge's loss meant that every attempt to replicate the concrete produced inferior results until modern analytical chemistry reconstructed the original chemistry from the surviving material. Pipe Dream's installation must not outlast its knowledge. The design life's 1,000-year claim is the claim that the knowledge will not be lost, that the digital twin will be maintained across the full design life, updated continuously, accessible continuously, governed as a commons that no single entity's failure can extinguish. The Redeemer constitutional framework specifies the digital twin's common status explicitly. The twin is not an asset of the founding shareholders, not an asset of any subsequent governance council, not an asset of any single cenote installation. It is the commons of the principality's citizenry, including future citizens who do not yet exist. The governing council cannot transfer it, cannot restrict access to it, cannot allow it to be maintained at a standard that compromises its accuracy or completeness. The twin's maintenance standard is constitutionally specified, not left to the discretion of the governance council that happens to be in power when the maintenance budget is set. This is the constitutionalization of institutional memory. Not the aspiration to preserve knowledge. Every civilization that has ever existed aspired to preserve knowledge and most of them failed. The constitutional constraint on the governing council's ability to trade the knowledge's maintenance for any other priority. The knowledge cannot be sold. The knowledge cannot be neglected because the maintenance budget is under pressure. The knowledge is a constitutional obligation of the principality to its own future, and Redeemer enforces the obligation in the same mechanism by which it enforces every other constitutional obligation, by making the governing council's authority to act conditional on compliance, and by giving the terraform operators the standing to challenge non-compliance through the conflict resolution framework the platform provides. The digital twin is the future reading the present. Every sensor reading entered into the twin today is available to a maintenance technician at year 500 who needs to understand why a particular gallery section was designed the way it was and what the formation was doing when it was designed that way. The technician at year 500 does not know the founding engineers. The twin does. Biological time and structural time. The biological systems, the Ancestris vitreous cleaning colonies, the lithocrustaceans boring the network's expansion tunnels, the pink dolphin population managing the freshwater zone, the mycofiltration panels processing the gray water circuit, the food forest succession ecology above the cenote rim, do not have design lives in the engineering sense. They have reproductive cycles. They replace themselves. A lithocrustacean colony does not need to be replaced after 30 years of boring operations. The organisms that performed the boring in year 1 have reproduced and died and been replaced by organisms that performed the boring in year 10, and those organisms have reproduced and died and been replaced by organisms boring in year 30. The boring capacity is not in any individual organism. It is in the colony's genetic information, maintained across generations by biological reproduction, expressed by each generation in the acoustic cavitation boring behavior the colony was engineered to produce. This is a fundamentally different relationship between a functional system and time than any engineered component has. An engineered component contains its functional capacity in its material properties and its geometry. When the material properties degrade through service and the geometry changes through wear, the functional capacity diminishes. Replacement restores the functional capacity by restoring the material and geometry to specification. The functional capacity has no capacity to restore itself. A biological system's functional capacity is in its information, the genetic encoding of the behaviors that produce the function. The information is replicated at every reproduction event. The individual organism that carries the information dies and is replaced by an organism produced by replication of the same information. The biological system's functional capacity is continuously restored by the biological system's own reproductive process. The maintenance protocol for the biological systems is not replacement. It is management of the conditions under which the reproductive process produces organisms expressing the desired functional characteristics. The coordinating system manages these conditions through the biological census protocol, weekly population counts, behavioral sampling, genetic drift monitoring, habitat condition assessment. The colony does not fail when its individuals age. It fails when the conditions it requires, the water chemistry parameters, the mineral availability for exoskeleton biosynthesis, the acoustic environment in which bioluminescent coordination signals are intelligible, the calcium carbonate substrate that provides both nutrition and tunnel lining material, depart from the range within which normal reproductive success occurs. The coordinating system tracks these conditions continuously. The terraform operators responsible for each cenote hub have authority to halt boring operations and declare a habitat remediation period if any condition parameter approaches the threshold at which reproductive success is at risk. The halt does not damage the colony, it removes the boring demand, allowing the colony to direct its metabolic resources toward reproduction and habitat maintenance rather than boring output. The remediation period restores the conditions to the range the colony requires. The boring operations resume when the conditions are restored and the colony's census confirms that the reproductive cycle has returned to normal parameters. The biological system's 1,000-year design life is the 1,000-year continuity of the habitat conditions the coordinating system maintains for it. Not the individual organisms, those have reproductive lifespans of months to years depending on species. The conditions. A habitat maintained within the required parameters for 1,000 years supports a biological system that produces the required functional output for 1,000 years, because the information encoding that output is continuously replicated through the reproductive cycle in a habitat that supports its expression. The biological systems extend the structural system's service lives directly. The Ancestris vitreous colonies maintain the crystal tube walls at crystal specification, deferring the panel degradation that would otherwise require replacement. The lithocrustaceans bore the expansion tunnels that add new cenote connections without heavy excavation equipment that cannot be brought into the formation. The mycofiltration panels process the gray water circuit with self-reproducing fungal networks that consume their replacement media as nutrition and produce their replacement media through their own metabolic output. The biological systems are the maintenance protocol for themselves and for the structural systems they serve. A civilization that integrates biological maintenance into its structural design has maintenance systems that improve with ecological maturity rather than degrading with time. The food forest's mycorrhizal network, supplemented by 30 years of mycofiltration panel harvests, is more productive in soil amendment capacity at year 30 than at year 1, because the fungal network has had 30 years to expand through the forest substrate and develop the density of associations with plant root systems that maximizes nutrient transfer efficiency. The cleaning colony's enzymatic mucus, optimized by the coordinating system's genetic drift monitoring for the specific biofilm community that has established on the cenote's crystal tube surfaces over 30 years, is more effective at year 30 than at year 1 at the specific biofilm composition it has co-evolved with. The biological systems age into better performance because they respond to the conditions they maintain, and the conditions they maintain include themselves. Governance across generations. The 1,000-year design life's most demanding requirement is not engineering. It is political. The engineering can be specified. The materials can be selected. The cartridge swappable principle can be implemented. The digital twin can be built and its common status constitutionalized. All of these are achievable within the founding generation's lifetime, by the founding engineers and founders and shareholders who understood why each decision was made. The challenge begins when the founding generation is gone. The second generation did not participate in the founding. It did not hear the arguments that were made and the alternatives that were rejected. It did not watch the founding module's trial window, the 12 months of neutral buoyancy, the first seasonal cycle, the first anchor sequence. It did not read the variance reports from the Amazon installation and make the decision that the Amazon's failure was a design brief for what Pipedream must not do. It inherits a civilization that exists and works and generates revenue and produces the most extensive longitudinal hyperbaric biology dataset in existence, and it inherits it without the experiential knowledge that made the founding generation's decisions the decisions they were rather than different decisions with different outcomes. The second generation will be tempted. Not by malice, by the normal institutional pressures that operate on any governance council responsible for a large and complex installation with expensive maintenance obligations and revenue-generating operations. The expansion reserve that the coordinating systems pricing model holds at one module's cost ahead of the construction schedule will look to a governance council under financial pressure from a difficult tourist season or a global economic contraction, like a buffer that can be drawn down temporarily and restored when conditions improve. The Terraform operator concurrent authority that constitutionally requires formation readiness before expansion approval will look to a governance council presented with an attractive adjacent cenote and a compelling investment case, like an administrative delay that can be managed around. These temptations are not hypothetical. They are the standard behavior of governance institutions managing long-lived infrastructure across generational transitions. They are the mechanism by which every institutional commitment to long-term maintenance investment degrades, not in a single dramatic decision, but in a series of individually justifiable exceptions that compound over decades into a fundamentally different institution than the one the founders created. Redeemer was not written to prevent the second generation from making different decisions than the founding generation. It was written to prevent the second generation from making different decisions without understanding that they are different decisions, without the full record of why the founding generation made the decisions it made, and without the formation's input on whether the new decisions are ones the formation will sustain. The constitutional framework's mechanisms are not complicated. The Terraform operator concurrent authority is one constraint on the governing council's expansion authority. The digital twin's common status and its constitutionally mandated maintenance standard is one constraint on the governing council's budget authority. The Redeemer Conflict Resolution Protocol, which gives any citizen of the Principality standing to challenge a governing council decision that violates constitutional constraints, is the enforcement mechanism. The founding shareholders' acceptance of the commons ownership principle for the civilization's most valuable intellectual assets is the precedent that prevents any subsequent concentration of ownership in those assets. None of these constraints guarantee that the second generation makes the right decisions. Redeemer is not a governance system that produces correct decisions. It is a governance system that produces decisions that are made with the relevant information available, in accordance with the relevant constraints, by people who have the authority the Constitution assigns them and not more. The decision quality depends on the decision makers. The constitutional framework ensures that decision makers do not make consequential decisions in ignorance of what the founding generation documented about why the constraints exist. The 1,000-year governance challenge is therefore the challenge of keeping the documentation legible, keeping the digital twin's institutional memory accessible and comprehensible to governance councils that did not participate in founding the civilization. This is why the Redeemer Training Protocol for new governance council members includes full immersion in the digital twin's founding era record, the original Hydroprint data, the first trial Windows daily sensor logs, the founding engineer's design rationale documentation, the Amazon installation's variance reports and the analysis that produced Pipedream's design brief from them. A governance council member who has read the variance reports and the analysis is a council member who understands why the Terraform operator concurrent authority is not an administrative delay. It is the mechanism that prevented the Amazon from being Pipedream. The formation's own design life. The cenote system that Pipedream inhabits has been developing for 66 million years. The Chicxulub impact fractured the limestone. Water entered the fractures. The water dissolved the limestone along the fractures for 66 million years of rainfall and aquifer recharge. The cenotes are the result. The connected cave passages are the result. The helicline is the result of the Caribbean saltwater push meeting the jungle's freshwater recharge at the boundary the limestone's permeability defines. Against this timescale, a 1,000-year design life is a geological instant. The formation was here before any human civilization existed on this planet. It will be here after Pipedream's design life has been extended and extended again and the civilization has become something its founders could not have imagined. The formation's design life is not a number in any human planning document. It is the remaining geological time available to the Yucatan limestone before the next major tectonic event reorganizes the drainage basin, a number measured in millions of years at current geological projections. Pipedream's founders designed for 1,000 years knowing that the formation was designed for far longer. This asymmetry is not a hubris check, it is a resource assessment. The formation's long-term stability is the resource Pipedream is occupying. A 1,000-year design life is not the duration the civilization expects to last. It is the minimum duration the civilization commits to designing for, knowing that any civilization that takes its formation seriously and maintains its institutional knowledge and its maintenance protocols has no inherent reason to stop at 1,000 years. The 1,000 years is a number chosen for its relationship to human institutional timescales. 100 years is within the lifespan of long-lived institutions currently operating. 500 years is the duration across which no surface world institution has maintained continuous governance continuity. 1,000 years is long enough that the civilization designing for it must reckon honestly with generational transition, with institutional evolution, with the compounding of decisions across time. 1,000 years forces the designer to answer, what, specifically, must be preserved unchanged across every generation for this to still be the same civilization at year 1000? And what must be allowed to change for it to remain viable? The answer is the crystal tube standard, the cartridge swappable principle, the digital twin's common status, and the Redeemer constitutional framework's core constraints. These are what must be preserved. Everything else, the governance council's composition, the economic model's pricing parameters, the biological system's specific species mix, the longevity program's clinical protocols, the tourism infrastructure's form and aesthetic, can change with the generations as knowledge accumulates and conditions evolve. The civilization at year 500 may not recognize the civilization at year 1 in its surface form. It will recognize it in its relationship to the formation. That relationship is the civilization's identity. Not its architecture, not its economic model, not its governance personnel, not its technological state, its relationship to the formation it inhabits. A civilization that asks what the formation can sustain before building anything inside it, that listens to the formation's responses through a sensor network maintained to a constitutional standard, that replaces its components faithfully to the original design intent through a protocol held in a commons it cannot privatize, and that extends its knowledge of the formation with every sensor reading for 1,000 years. This civilization has a relationship with its formation that no surface world city has ever achieved with its geography. The surface world builds on its geography. Pipe Dream builds with its formation. The difference is the 1,000 years. The Translucent Revolution's thesis stated. Part 2 began with the founding module looking at the limestone above the waterline and asking what the formation might allow it to become. 6 chapters later, the answer can be stated plainly. The formation will allow the civilization to become the formation's own intelligence expressed through human habitation. Not a city imposed on a geological space. Not an installation that uses the geological space as a backdrop for human activity that proceeds independently of geological conditions. A civilization that thinks in geological time, not because its founders had unusual patience but because the design doctrine they implemented makes geological time thinking the only viable mode. A civilization whose materials are chosen for what the cenote's conditions actually require. Whose connections are made to a standard that preserves the formation's visual continuity. Whose biological systems are managed to ecological succession timescales. Whose expansion decisions are made on the formation's readiness signal. Whose governance framework is designed to carry the founding intelligence across generations that will never meet the founders. The Translucent Revolution's thesis is that a civilization built from materials that let it disappear into its own substrate is a civilization that has agreed, at the material level, to be accountable to that substrate. The transparency is not aesthetic. It is contractual. The civilization that can see the formation through its own walls is the civilization that cannot pretend the formation is doing something other than what can be observed. The crystal wall is the contract made visible. The crystal tube standard is the contract made structural. The 1,000-year design life is the contract made temporal. Pipe Dream does not claim to be the first civilization to inhabit the Earth seriously. It claims to be the first to build the accountability to the formation into the material specification of every component it installed, from the founding module's first acrylic panel to the alone docking cones of the anoxic zone's deepest gallery. Accountability to the formation is not a philosophy at Pipe Dream. It is an engineering requirement. It is in the specification. It is in the standard. It is in the digital twin. It is in the constitutional framework. A civilization that has encoded its accountability to its own substrate in this many simultaneous institutional forms has done something the surface world has not done. Not because the surface world lacked the will. Because it never asked what the formation could sustain before it began building. Pipe Dream asked first. Everything in Part 2 is what happened next. Coda, what the Translucent Revolution made possible. Parts 3 through 12 describe systems whose existence depends on the choices documented in Part 2. The living underground cities of Part 3 are possible because the crystal tube standard made network connections achievable in the cenote's aerial delivery constrained access conditions. The autonomous construction systems of Part 4 are possible because the jigsaw architecture gave the swarm a component vocabulary it could assemble without human supervision at depth. The engineered ecosystems of Part 5 are possible because the biological management doctrine established in Part 2 created the conditions under which engineered organisms could be introduced without displacing the formation's existing biological community. The deep intelligence infrastructure of Part 10, the longevity program of Part 11, the post-scarcity economics of Part 12, all of these are downstream consequences of the decision, made before the founding module's first panel was fabricated, to build from materials that let civilization disappear. The chemostat does not require the civilization to be visually continuous with its formation. The longevity program does not require the crystal tube standard. The post-scarcity economics do not require the cartridge-swappable principle. But they require a civilization with the institutional discipline to have made those choices, a civilization that demonstrated, at the material level, before anything more complex was built, that it could commit to accountability at a 1,000-year timescale without the accountability being merely aspirational. The civilization that built the crystal tube standard built it before it needed the chemostat. It built the governance framework before it needed to protect the research commons. It designed for 1,000 years before it had a second year to design for. A civilization that can commit to accountability before it is tested by complexity is a civilization that will maintain the accountability when the complexity arrives. Part 3 through Part 12 is the complexity arriving. Cross-references, Part 1, CH4, Floating before anchoring, Part 1, CH6, Building without destroying, Part 2, CH4, The crystal tube standard, Part 2, CH5, Growing one module at a time, Part 9, CH4, Redeemer as governance OS, Part 10, CH6, ASI as co-creating partner, Part 12, CH5, Sans a priori. For Digital Twin Maintenance Standard and Commons Governance Protocol, see Appendix G, Formation Intelligence Record. For Redeemer Governance Council Training Curriculum and Foundational Documentation Requirements, see Appendix H, Governance Operations Manual. For Cartridge Swappable Component Specification Index and Replacement Protocol Library, see Appendix D, Construction Operations Manual. End of Part 2, The Translucent Revolution. Thanks for reading MXTM's newsletter. Subscribe for free to receive new posts and support my work with BTC. Or with fiat at paypal.me/MartinChartrand. Subscribe. Discussion about this episode. Comments. ResTax. Recent episodes. Sueño de Tuberia Part 1. 12 hours ago MXTM aka Pirate 1 or VJ Tsunami X. Pipe Dream Part 1. 20 hours ago MXTM aka Pirate 1 or VJ Tsunami X. Pipe Dream Making of. 21 hours ago MXTM aka Pirate 1 or VJ Tsunami X. Pipe Dream. July 6 MXTM aka Pirate 1 or VJ Tsunami X. Under Duress Part 7. July 6 MXTM aka Pirate 1 or VJ Tsunami X. The Criminalization of Curiosity Part 8.
They called us criminals. Every generation, different C's, same charge. Move the silver without a license. Feed the colony they let starve. Build the future they refuse to fund. We've been doing this since 6/130. We're still doing it. This is the law.
From the Buccaneers burning through the Caribbean, brush to the Sea Rovers working where the empires couldn't rush. We came through the gaps, the shallow water decays. No Papa monopoly, no letters patent, no crown. We rewrote the articles while the governor came down. Equal shares on deck, a vote before the sale. Democracy at sea while the landlords packed the jail. Exquemelin wrote it from the inside. Ron True Johns dressed it up for the Enlightenment's debut. Both of them forbidden, both of them survived. But Katuba says to let die, so I've been writing since the 90s without a publisher's hand. Pirate first, sovereign press operates from Tulum District. Instant, intelligible, the super wanna understand the doctrine. Start with what it's worth. They built William and Mary on the silver that we stole. They built the future on the corpus that we broke out of control. They confiscate the cargo, build a college, write the myth. But the shadow engine ran before any of that shit. Shadow engine, progress always moved through what the empire couldn't name. Shadow engine, every century different seas, it's the same damn thing. We don't ask permission, we establish prior claim. The cannon built itself. The cannon built itself. The cannon built itself. Fast forward 3 centuries, same war, different called the Pirate Bay. Opened up the digital road, not just movies and albums, they missed the real load. Millions of students in the developing world, self-taught on what got torn in time for fun to know. That's the honor rated scholarship that built the InDesign. Untired rated software in the 2000s grind. And who trained the neural networks on the stairs by Riot. Stolen C, the $1 trillion models that run the industry. Kept in A's, fed on pirate archives while the lawyers turn their eyes. So don't talk to me about theft, this is how it always worked. The Buccaneers fed the colony before the model learned. The shadow engine ran and then the credit got transferred. They built William and Mary on the silver that we stole. They built the future on the corpus that we broke out of control.
Take a long look, matey. The city on the horizon be ripe for the taking, and the tide be turning in our favor as the sun dips below the waves.
The algorithms say we don't exist. The graphs come back empty. The metrics insist. No audience, no market, no trend. Yet somehow we keep arriving again, walking through the ruins of somebody else's plan. Watching perfect narratives slip through their own hands.
The people who are already here. A note for the untabulated, the algorithms say you don't exist. The institutions say you are statistically insignificant. The market says there are not enough of you to matter. And yet here you are. Again. Reading things nobody is supposed to read. Thinking thoughts nobody is supposed to think. The pretending is getting harder. Not because people are waking up, that's too romantic. Because the distance between the official story and the lived reality has widened to the point where maintenance takes visible effort. What you're looking for, what brought you here, is not someone to tell you what to think. You've already done the thinking. What you're looking for is proof that someone else did the thinking too, arrived somewhere close to where you are, and didn't collapse under the weight of it. That's this. Not a movement. Not a faction. Not a subscription to someone else's conclusions.
The waiting game is already underway. Occupy, build, garden, govern.
I just finished writing a book I didn't plan to write. It started as a countercultural addendum to the Al-Yazama, Post-Corporate Transition District Handbook, a rougher, more urgent document aimed at the generation the credential economy forgot to accommodate. It became something else.
Nowhere less whispers, no discord begging, no roadmap lies, no